Hello there and welcome to Science for Sleep, where we take complicated ideas, lower the lights, and give them enough room to become understandable without demanding that anyone stay sharply awake. Tonight, we are heading far beyond the familiar planets of our solar system to visit a place that is small, strange, and very difficult to imagine. It is a planet called Draugr, also known by the less memorable catalogue name PSR B1257+12 B. The catalogue name sounds as though someone dropped a box of letters and numbers down a staircase, which is fairly normal in astronomy. The name Draugr is easier to remember, though perhaps not especially cheerful. It comes from an undead figure in Norse tradition, and it suits a world that circles the remains of a dead star. Draugr is often introduced as the lightest confirmed planet known beyond our solar system, although it is safer to say that it is one of the lightest confirmed exoplanets ever measured. The universe is large enough to contain countless smaller objects that we have not detected, and astronomers are usually careful about declaring that anything is the absolute smallest, largest, oldest, or strangest forever. Space has a habit of correcting confident statements. Still, Draugr is remarkably light by planetary standards. Current catalogues give it a mass of about 2/100ths of Earth's mass. That places it in roughly the same broad range as a few of the larger moons in our own solar system, rather than the major planets. It travels around its pulsar in just over 25 days, at an average distance of about 19/100ths of the distance between Earth and the Sun. It was identified through pulsar timing, a method that relies not on seeing the planet directly, but on measuring tiny changes in the arrival of radio pulses from the object it orbits. Before we go any farther, where are you listening from tonight? Perhaps you're in a quiet room with the lights already off. Perhaps you're still awake at a desk telling yourself that one more video will somehow make tomorrow morning easier. Perhaps it is raining outside. Perhaps the window is open. Or perhaps you can hear the low background noise of a city that has not quite decided to sleep. And what time is it where you are? Draugr completes an entire year in a little more than 25 Earth days, so the answer would be rather different if you were somehow asking the same question from its surface. A birthday there would arrive so often that even the most enthusiastic person might begin to find cake administration exhausting. If you find these slow journeys through science calming, interesting, or useful for easing the mind away from the day, you can like the video and subscribe to the channel. It helps other curious listeners find this quiet corner, and it tells the mysterious machinery behind the screen that gentle explanations of distant planets are worth sharing. You're also welcome to leave a comment with your location and local time. It is always interesting to see how many different parts of Earth can meet in the same discussion about a planet that none of us can see with our own eyes. Now, settle into a comfortable position and let your attention loosen a little. There will be numbers, but they will not be examined later. There will be unfamiliar terms, but none of them need to be memorized. Draugr is a useful place to visit because it challenges several ordinary ideas at once. We tend to imagine a planet as something substantial. It should be large enough to become a clear round world, heavy enough to pull moons into orbit, and bright enough to appear in a telescope if we build a sufficiently large one. We also tend to imagine planets around normal stars, stars like the Sun that spend billions of years producing steady light and warmth. Draugr does not fit comfortably into either picture. Its central object is PSR B1257+12, a millisecond pulsar. A pulsar is a neutron star, the extremely dense remnant left after a massive star dies. It is not a calm yellow sun. It is the compact core of a star that went through a catastrophic ending and left behind an object with more mass than the Sun packed into a region roughly comparable in size to a city. This remnant spins rapidly and produces beams of radiation. When one of those beams sweeps across Earth, radio telescopes receive a pulse. The effect is often compared to a lighthouse, although a lighthouse usually has the courtesy to rotate at a pace visible to the human eye. PSR B1257+12 rotates once every 6.2 milliseconds. That means it completes more than 160 turns every second. It is difficult to picture an object with stellar mass rotating so quickly, which may be just as well, because the mental image tends to make ordinary household appliances seem wonderfully safe. The pulses from a millisecond pulsar can arrive with extraordinary regularity. That regularity is the reason astronomers can notice planets around one. Draugr is far too distant, too small, and too faint to photograph as a tiny disk. No telescope has taken a family portrait of the planet next to its pulsar. Instead, astronomers detected a subtle pattern in timing. As a planet orbits, its gravity causes the pulsar to move slightly around the shared centre of mass. The pulsar does not remain perfectly fixed while the planet circles it. Both objects move, although the much smaller planet does nearly all the travelling. That slight movement changes the distance the radio signal must cross before reaching Earth. Sometimes the pulsar is a little closer, and the pulses arrive a little earlier. Sometimes it's a little farther away, and they arrive a little later. By measuring these changes with great precision, astronomers can infer that an unseen companion is present. This is one of the appealing things about astronomy. A planet can be discovered without being seen. Its existence can be read from the regular ticking of a dead star that is being gently pulled from side to side. The signal does not arrive with a label saying, "Small planet located here." Astronomers must build a model, compare predictions with years of observations, rule out errors, and check whether the pattern repeats in the way an orbit should. The result is less like taking a photograph and more like hearing a clock through a wall, then realizing that someone on the other side is moving it back and forth by a tiny amount. The system became historically important because it contained the first confirmed planets found beyond the solar system. The two larger planets were reported in 1992 after precise timing observations with the Arecibo radio telescope. Evidence for the much smaller inner world followed in 1994, alongside confirmation that the larger planets were interacting gravitationally in the predicted way. That interaction mattered because it helped show that the timing signals were truly caused by planets, rather than by some unknown behaviour of the pulsar. The discovery established that a neutron star could host a planetary system, and that planets could exist in conditions very different from those around the Sun. This was not the kind of planetary system many people expected to find first. Before exoplanets became a large field, it was reasonable to imagine that the first confirmed worlds around other stars would resemble familiar members of our own system. Perhaps astronomers would find a giant planet like Jupiter around a calm star nearby. Instead, the first confirmed system included rocky, low-mass planets circling a pulsar. The universe did not begin the exoplanet era with a reassuring copy of home. It began with 3 planets around an object created by stellar death. Draugr is the innermost and smallest member of that known group. Its 2 larger neighbours are commonly called Poltergeist and Phobator. The pulsar itself received the name Lich. These names were selected as part of an international naming effort, and the theme is not difficult to detect. A Lich is an undead being, a Draugr is a reanimated figure from Norse stories, a Poltergeist is a noisy spirit, and Phobator is associated with nightmares. Astronomers are often described as serious people, but their naming choices occasionally suggest that someone gave a research committee access to a shelf of fantasy novels shortly before a deadline. The names also reflect something real about the system. These are worlds around a stellar remnant, exposed to an environment unlike the gentle daylight we know. Calling Draugr light does not mean it would float away or feel weightless in every sense. Mass and weight are related, but they are not the same thing. Mass describes how much matter an object contains. Weight depends on gravity. Draugr has only about 0.02 Earth masses, but we do not have a direct image or a measured radius from a transit, so its surface gravity cannot be stated with the same confidence as its orbital period. NASA lists an estimated radius of about 0.338 Earth radii and classifies it as terrestrial, but that radius is model-based rather than a direct view of the planet. The surface could be a solid body, and its local gravity might still be strong enough to keep material firmly in place. Small does not automatically mean loose or fragile. Our own moon is much less massive than Earth, yet rocks on the moon do not drift off into space simply because they feel underappreciated. The word planet also carries more uncertainty than it first appears to. In ordinary conversation, the category seems simple. Mercury is a planet, Earth is a planet, and Jupiter is very definitely a planet. Farther out in the universe, the boundaries become less comfortable. Objects can form in disks around stars, survive explosions, emerge from debris, or occupy mass ranges similar to moons. Draugr is accepted as a confirmed planet in major exoplanet catalogues, but its unusual host and low mass make it a useful reminder that nature does not organise itself according to the tidy examples in a school diagram. There is also the question of how a planet like this came to exist at all. The massive star that produced the pulsar would have passed through violent stages. A supernova can eject enormous amounts of material and alter the gravitational structure of an entire system. Any original planets would face intense radiation, shock waves, and the sudden loss of stellar mass. A planet that remained in orbit would need to survive that event under very particular conditions. Another possibility is that the current planets formed later, from a disk of material created after the neutron star was already present. In that case, Draugr may be a second-generation planet, built from matter associated with the destruction or interaction of earlier stars. It could be less a survivor than a product of the aftermath. Astronomers have not settled every detail of that formation story. The broad possibilities include survival from an earlier planetary system, formation from material after the supernova, or formation through later interactions involving a companion star and an accretion disk. The system's architecture, especially the nearly coplanar orbits of the two larger planets and their dynamical relationship, supports formation in a disk. That does not automatically tell us exactly when the disk formed or what sequence of events produced it. The evidence narrows the story, but it does not turn the past into a recording we can replay. For tonight, it is enough to begin with the scale of the object itself. Earth has a mass of roughly 6 sextillion metric tons. Writing that number out creates a long row of zeros and does very little to make it feel real. Draugr, at about 2% of Earth's mass, is vastly lighter than our planet, while still containing an amount of material that defeats any everyday comparison. It is light only in relation to planets. If someone placed Draugr on a bathroom scale, the main problem would not be choosing between kilograms and pounds. The main problem would be the immediate destruction of the bathroom, the scale, the surrounding region, and the general usefulness of the experiment. Compared with Earth, Draugr may seem more like a planetary fragment. Compared with an asteroid, it is enormous. Ceres, the largest object in the asteroid belt, has only a small fraction of Draugr's mass. Pluto is also lighter than Draugr. The planet therefore occupies an interesting middle range. It is much smaller than Earth, and smaller than Mars, yet more massive than the dwarf planets most people know by name. It may resemble a large rocky body somewhere between the scale of Pluto and Mercury, although its actual composition remains uncertain. We know its gravitational effect. We do not possess a sample, a photograph, or a spectrum of a visible atmosphere. That gap between what is known and what is imagined is important. Artwork of pulsar planets often shows dark, rocky ground, dramatic auroras, glowing horizons, and the narrow beams of the pulsar crossing the sky. Such images are useful for giving the mind something to hold, but they are not photographs. We do not know what colour Draugr would appear from nearby. We do not know whether it has a smooth surface, ancient impact basins, exposed metal, glassy rock, or no stable surface in the form people usually imagine. We do not know whether it has retained any atmosphere. The pulsar environment exposes the planets to energetic radiation and particle winds, which would make atmospheric survival difficult. However, The exact conditions depend on the planet's composition, magnetic field, history, and interaction with the pulsar's output. Even its name requires a small clarification. In current astronomical catalogues, the planet is usually written as PSR B1257+12 B, with a lowercase b. Some older discussions call it PSR B1257+12 A because it was the first planet outward from the pulsar, and the system's planets were historically labelled A, B, and C. The title we're using includes that older designation. Both labels point to the same tiny inner world. Astronomical naming systems develop over time, and they do not always move gracefully. Occasionally, a planet can have a mythological name, a catalogue name, and a historical letter, all before anyone has worked out what its surface is made of. The distance adds another layer of separation. The pulsar lies hundreds of parsecs away, which means its radio pulses have travelled for well over 1,000 years before reaching our instruments. The exact distance estimate varies among catalogues and measurements, but it is far beyond any practical journey. When a telescope records a pulse from PSR B1257+12, it is not detecting the system as it is tonight. It is receiving information that began crossing space many centuries ago. Draugr has completed countless 25-day orbits, while that signal travelled towards Earth. No spacecraft is heading there, and none could reach it on any useful human timescale with present technology. Our connection to Draugr is entirely through measurement and inference, yet the planet has changed how we think about planetary systems. It showed that worlds can appear where earlier expectations gave them little room. It demonstrated the power of timing as a detection method. It also widened the question of what counts as a normal place for planets. Once a world can orbit a rapidly spinning neutron star, the range of possible planetary homes becomes much broader than a collection of calm, sun-like stars. There is a practical reason to begin with this very small planet, rather than one of the thousands of larger exoplanets now known. Draugr forces us to pay attention to the limits of detection. Large planets are easier to notice. They pull more strongly on their stars, block more light during transits, and create larger signals. A body with only a small fraction of Earth's mass is much harder to find. In this case, the pulsar provided an unusually precise clock, and the planet announced itself by disturbing that clock. Draugr did not need to shine, it only needed to tug. That quiet tug is the starting point for everything that follows. It gives us the planet's orbital period, helps constrain its mass, and places it within a system whose history includes stellar death, rapid rotation, and the rebuilding or survival of planetary material. From one repeating delay in a radio signal, astronomers were able to identify a world that could never have been found through ordinary sight alone. So, as you listen, there is no need to picture Draugr as a fully known landscape. It is better to hold a simpler image. Far away, a dense stellar remnant turns more than 100 times each second. Its radio beam sweeps across space with dependable timing. Around it moves a small body, completing an orbit in a little over 25 days. The planet's gravity shifts the pulsar by a tiny amount, and that shift changes the arrival time of the pulses reaching Earth. The change is small, but it repeats. Repetition becomes evidence, and evidence becomes a planet. That small repeating tug leads us toward Draugr itself, a planet whose importance is almost completely out of proportion to its size. In a system containing a rapidly spinning neutron star and 2 planets several times as massive as Earth, the smallest member would be easy to overlook. It produces the weakest signal, occupies the tightest orbit, and offers the fewest obvious clues about its physical appearance. Yet it is precisely this lack of size that makes it so useful. Draugr shows how far the idea of a planet can be stretched before it begins to resemble the large moons and dwarf worlds of our own solar system. The official catalogue designation is PSR B1257+12 B. Older scientific discussions often call it PSR B1257+12 A, because the 3 companions were originally labelled according to their positions in the system, rather than the naming convention now commonly used for exoplanets. The current lowercase letter b does not mean it was the second planet discovered, and the older capital A does not describe a different object. Both labels refer to the same inner companion, orbiting closer to the pulsar than Poltergeist and Phobator. Astronomical names are meant to reduce confusion, though they occasionally achieve this by creating several correct ways to say the same thing. Draugr is at least easier to pronounce once you have heard it a few times. The International Astronomical Union adopted the name in 2015, drawing it from the undead beings of Norse mythology, while the pulsar received the name Lich. The mythological name sounds dramatic, but it does fit the basic arrangement. Draugr circles the remnant of a star. The original star no longer exists in its earlier form. Its outer layers are gone, and the dense core left behind has become a neutron star. That core spins every 6.2 milliseconds and sends radio beams across space. A complete rotation takes less time than the blink of an eye by such a wide margin that a blink begins to look like a lengthy administrative procedure. The planet beside it is not orbiting a sleeping object or a cold lump of ash. It is moving around an active pulsar whose radiation and particle output create an environment very different from the one surrounding Earth. Draugr's measured mass is about 0.02 times the mass of Earth. Put another way, Earth is roughly 50 times more massive. The estimate comes from the effect of the planet's gravity on the pulsar's motion, not from placing the planet on an unusually ambitious set of scales. In exoplanet catalogues, the value may be described as a minimum mass, or as a mass based on the system's orbital solution, because the exact interpretation of timing measurements can depend on orbital inclination. Even with that caution, the object is clearly far lighter than Earth, Venus, Mars, or Mercury. NASA classifies it as terrestrial, and lists an estimated radius of about 0.338 Earth radii. Though the radius is not a direct measurement from an image or a transit, a radius of roughly 1/3 of Earth's would make Draugr similar in scale to some of the larger moons in our solar system. Its mass belongs in the same broad range as the largest moons rather than the major planets. Those comparisons are helpful, but they should not be taken as proof that Draugr looks like any familiar moon. Two objects can have similar masses and very different compositions. One may contain a large iron core, another may be rich in silicate rock, and another may include substantial amounts of ice or other volatile material. Around a pulsar, long-term exposure to radiation and energetic particles could also alter a surface and remove lighter materials. The comparison tells us the size of the problem, not the answer to it. If Draugr could be placed next to Earth, our planet would dominate the view. Using NASA's estimated radius, Draugr would have a diameter of roughly 4,300 kilometers. Although that figure follows from a model rather than a direct measurement, it would be larger than Pluto and smaller than Mercury. It would not look like a speck. It would be a proper world-sized object with enough gravity to pull itself toward a rounded shape, assuming the estimated radius is reasonably close. Tiny is therefore a relative term. Draugr is tiny beside Earth, and Earth is tiny beside the Sun, while the Sun is not particularly large by the standards of massive stars. Astronomy is very good at making every object feel inadequate in the presence of another object. Its orbit is much better constrained than its surface. Draugr travels around the pulsar in about 25.3 Earth days. Its average orbital distance is listed as roughly 0.19 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, so Draugr circles at less than 1/5 of that distance from its host. In our solar system, that orbit would lie well inside Mercury's path. Mercury takes about 88 Earth days to go around the Sun. Draugr completes more than 3 of its own years in the same amount of time. That does not mean Draugr experiences a hotter version of Mercury's daylight. A pulsar does not shine like the Sun. The energy arrives in different forms, including radio emission, X-rays, high-energy particles, and a pulsar wind. The total conditions at the planet depend on the pulsar's spin-down power, the geometry of its beams, the interaction of particles with the planetary surface, and any atmosphere or magnetic field the planet may possess. Astronomers have detected X-ray emission from PSR B1257+12, although the system remains faint and difficult to characterize in detail. Describing the planet as simply hot or cold would therefore hide more than it explains. Its surface might be heated unevenly, stripped of an atmosphere, or altered by radiation in ways that have no close equivalent on Earth. The orbit appears nearly circular in catalogue summaries. That matters because a highly elongated path would carry the planet through large changes in distance and exposure during every revolution. A near-circular orbit keeps its separation comparatively steady. It also contributes to the impression that the system was shaped by an organised disk, rather than by three unrelated objects captured at random. The strongest evidence for a disk origin comes from the two larger planets, whose orbits are nearly cut-planar and close to a 3-to-2 period relationship. Draugr is too light to create equally obvious mutual perturbations, but it belongs to the same compact arrangement. From Draugr's position, the pulsar would not resemble the Sun hanging as a broad yellow disk. A neutron star is only about the size of a city, although it contains stellar mass. At a distance of 0.19 astronomical units, its visible body would still appear extremely small. What might dominate would be its energetic output rather than its apparent width. The sky could be affected by radiation, particle interactions, and perhaps auroral activity if the planet had a magnetic field and some form of atmosphere. No observation has shown us such a sky, so any detailed scene belongs to informed illustration rather than measured fact. There is no confirmed colour palette for Draugr, no known cloud pattern, and no photograph of a horizon under the pulsar. The absence of a direct picture is worth keeping in mind because names and artwork can make an object feel more familiar than it is. Once a planet is called Draugr, it is easy to imagine a dark, frozen world with a grey surface and a narrow beam passing overhead. The actual planet might be darker, brighter, smoother, rougher, denser, or more chemically unusual than that image. It may have been resurfaced by impacts early in its history. It may have lost volatile compounds. Its crust may contain material formed in a disk very different from the disk that produced Earth. We know the rhythm of its orbit far better than we know the nature of the ground. Whether Draugr has an atmosphere is unknown. A small body has a weaker gravitational hold on gas than a larger planet, and the surrounding pulsar environment would make atmospheric retention difficult. High-energy radiation can heat the upper layers of an atmosphere and allow molecules to escape. A pulsar wind can also interact with gas and a magnetic field, gradually stripping material away. Still, difficult is not the same as proven impossible. The result would depend on the original amount of gas, the planet's composition, the strength of its magnetic protection, and the length of time it has spent in its present state. Without transit measurements or direct spectroscopy, astronomers cannot point to a confirmed atmosphere or confidently describe its pressure. The same uncertainty applies to its internal structure. If Draugr formed from material left after a stellar interaction, it might contain a different mixture of elements from the planets around the Sun. A metal-rich disk could produce a dense body with a large iron fraction. A disk containing lighter rocky material could produce something closer to a silicate world. If the planet survived from an earlier system, its composition might reflect conditions around the pulsar's original stellar form. Each scenario changes the likely surface and interior. The measured mass alone cannot choose between them. There is also no reliable reason to assign it an Earth-like day. The 25.3-day period describes its year, meaning the time required to complete one orbit. Its rotation period, the length of a day on the planet itself, is not established by the timing data. Because Draugr orbits close to a compact and massive object, tidal effects may have altered its spin over long periods, perhaps even pushing it toward a locked state in which the same side faces the pulsar. That is a reasonable possibility, but it is not a measured fact. A careful description must leave the length of its day open rather than quietly giving it one. The planet's neighbours help establish its place in the system. Poltergeist, or PSR B1257+12 C, has a mass of about 4.3 Earth masses and an orbital period of roughly 66.5 days. Phobator, or PSR B1257+12 D, is about 3.9 Earth masses and takes a little more than 98 days to orbit. Both are therefore hundreds of times more massive than Draugr. They are not gas giants in the Jupiter range, but rocky or super-Earth mass companions. Their gravitational interaction has been detected in the pulsar timing data, allowing astronomers to estimate their true masses and orbital inclinations. Draugr is so much lighter that it does not take part in the detectable orbital conversation with the same force. Imagine 3 people moving a heavy table. 2 are clearly shifting the weight, while the third is touching one corner with a single finger, and still technically contributing. The planet's small gravitational influence creates a timing pattern, but the larger companions produce stronger signals and measurable interactions with one another. This difference explains why the 2 larger planets were announced first in 1992, while the tiny inner object was reported as part of the 1994 confirmation work. The 1994 result did more than add another dot to the system. The larger pair have orbital periods close to a 3:2 ratio, so astronomers predicted that their mutual gravity should produce specific changes in the pulse arrival times. Those changes were detected after continued observations, providing powerful confirmation that the signals came from real planets. The same work reported the moon mass inner companion. The system therefore became the first confirmed planetary system beyond the Sun, and its smallest member helped show that the architecture extended inward to a remarkably low mass. At the time, this was an uncomfortable discovery in the most productive sense. Planets were expected to form around ordinary stars in disks of gas and dust. A millisecond pulsar was an old neutron star that had probably been spun up by receiving matter from a companion. The presence of several low-mass planets demanded an explanation. Either planetary bodies had survived conditions that seemed capable of destroying them, or new planets had formed after the original star's violent transformation. Later work on the system's distance, motion and orbital arrangement has supported the idea that the planets formed in a disk, possibly one produced through the disruption or evaporation of a stellar companion. The exact history remains debated, but random capture is not the leading picture. Draugr's survival also needs to be described carefully, because the word suggests that the planet was present before the neutron star formed. That is only one possibility. If it formed after the supernova or after a later interaction involving a companion, then it did not survive the pulsar's birth as a finished planet. Its raw material survived or arrived later, gathered into a disk, collided, accumulated, and eventually became the object now detected. In that version of events, Draugr is not an ancient planet that endured a stellar explosion. It is a younger world assembled near the remnant. The distinction is important, and will become more useful when we look at the possible origins of the entire system. Whatever its history, the planet now occupies a stable and repeated path. Every 25.3 days it returns to the same stage in its orbit. Its gravity moves the pulsar around the system's shared centre of mass. That movement is extremely small because the pulsar is immensely more massive, but the radio pulses are regular enough for the effect to be measured. We are not watching Draugr cross the face of its host, and we are not separating its light from the pulsar. We are following the consequences of its mass. This method gives the planet a strange kind of visibility. Draugr is invisible as a world, but clear as a pattern. It exists in a schedule of early and late arrivals. The planet's year is recorded not by seasons or changes in reflected light, but by the repeated displacement of a stellar remnant. If the pulsar were a less reliable source, the signal might disappear into noise. If Draugr were much lighter, the effect might fall below our ability to detect it. The discovery sits at a fortunate meeting point between a very small planet and a very precise natural clock. A world like this also changes how we use the word lightest. It is one of the lowest mass confirmed exoplanets in major catalogues. but that description partly reflects what our instruments can find. There are almost certainly smaller planets elsewhere. There may be asteroid-sized bodies orbiting stars and stellar remnants throughout the galaxy. Some pulsars show evidence of debris or disks, and small bodies can be extremely difficult to detect unless they produce a convenient timing effect, transit, or other measurable disturbance. Draugr is not necessarily close to nature's lower limit for planet formation. It is close to the lower limit reached by a particularly successful observation. The boundary between a planet and a large minor body is not determined by mass alone. In our solar system, the term depends partly on orbit and dynamical context. Exoplanet catalogues must work with objects detected under very different circumstances, often without direct images. Draugr is treated as a confirmed planet because it occupies a regular orbit around the pulsar and is understood as part of a planetary system. Yet its mass invites comparisons with moons, and those comparisons reveal how strongly categories depend on location. Move a large moon away from its planet and place it in an independent orbit around a star, and our language for it may change even though the object itself does not. The planet is sometimes described as doomed because of its exposure to radiation from the pulsar. That wording is effective for headlines, but it can imply an immediate destruction that is not observed. Draugr has maintained its orbit for the duration of our measurements, and the system is old. The planet may be airless, irradiated, and chemically altered, but it is still there. Solid rock and metal can remain in environments that would be lethal to familiar life. A place can be hostile without being temporary. The universe contains many durable objects that would be very poor choices for a holiday. Life, at least life resembling organisms on Earth, would face severe problems. The planet is small, the radiation environment is intense, and a stable protective atmosphere is uncertain. Liquid surface water, ordinary photosynthesis, and a mild climate are not reasonable assumptions. More speculative ideas sometimes consider whether thick atmospheres, deep oceans, or subsurface environments could protect life on pulsar planets. But there is no evidence that Draugr has any of those features. Its value does not depend on habitability. A planet can be scientifically important without being a possible home. Draugr matters because it demonstrates that planet-sized bodies can exist in a system shaped by extreme stellar evolution. It expands the known range of planetary masses. It shows the sensitivity of pulsar timing. It also prevents the story of exoplanets from becoming too tidy. The first confirmed system was not a copy of the solar system. Its smallest member was not an easy target orbiting a gentle star. It was a barely detectable companion close to a neutron star, found through the careful measurement of radio pulses. For the moment, we can leave its unknown surface unpainted. There is no need to decide whether it has black plains, metallic cliffs, frozen deposits, or a sky filled with auroras. Those details would be guesses. The secure picture is simpler: a body with about 2% of Earth's mass, moving on a nearly circular orbit that lasts a little more than 25 days, accompanied by two larger planets, all travelling around a millisecond pulsar about 710 parsecs from Earth. The object at the centre of Draugr's orbit is easy to describe badly. Calling it a dead star makes it sound inactive, like a cold piece of material left behind after the useful part of the star has ended. Calling it a lighthouse makes it sound large, slow, and reassuring. PSR B1257+12 is none of those things. It is a neutron star, the compressed core left, after a massive star reached the end of its life, and it rotates so quickly that the word spinning begins to feel insufficient. One complete turn takes about 6.2 milliseconds. In a single second, it rotates roughly 161 times. During the time it takes to blink, it may have completed dozens of rotations without showing the slightest concern for how unreasonable this appears. The name Lich was approved through the International Astronomical Union's 2015 Name Exoworlds campaign. In fantasy stories, a Lich is an undead being that continues functioning after death, usually with more ambition than anyone around it would prefer. The name suits a stellar remnant that has stopped producing energy through ordinary nuclear fusion, yet remains active through its rotation, magnetic field, and streams of energetic particles. The official catalogue designation remains PSR B1257+12, and the same object is also known as PSR J1300+1240. The two scientific names are based on its position in the sky using different astronomical coordinate reference systems. Astronomers have managed to give one object three names while still having no simple photograph of it, which is an impressive demonstration of administrative progress. A neutron star forms when the core of a sufficiently massive star collapses. The original star may have been enormous, but the remnant is typically only around 20 kilometers across. Within that city-sized volume can be more mass than the Sun. Matter is pressed into conditions that cannot be reproduced in an ordinary laboratory, and gravity at the surface is extraordinarily strong. PSR B1257+12 is generally analysed by assuming a neutron star mass of about 1.4 suns, although its exact mass has not been determined as directly as the masses of some neutron stars in tight stellar systems. The important point is that Draugr and its neighbouring planets orbit something with stellar mass packed into a region smaller than many cities. It is tempting to picture a neutron star as a giant ball of ordinary neutrons, neatly stacked together like tins in a very dense cupboard. The real structure is more complicated. The name tells us that much of the material has been forced into a state dominated by neutrons, but it does not mean every region contains one simple, uniform substance. Pressure changes enormously between the surface and the centre, and the behaviour of matter at the deepest levels remains an active area of research. What astronomers can say with confidence is that these objects are among the densest forms of matter that can be observed directly. The collapse also helps explain rapid rotation. A large star rotates before it dies. When its core contracts to a much smaller size, conservation of angular momentum can make the remnant spin faster, in the same broad way that a skater rotates more quickly after pulling in their arms. That comparison is helpful, although the skater is rarely reduced to the diameter of a city, or given a magnetic field capable of controlling charged particles across an enormous surrounding region. Neutron stars can be born rotating quickly, but millisecond pulsars are commonly understood to have received an additional boost later in their lives by taking material from a companion star. This process is often called recycling. A neutron star in a binary system can pull gas from its companion. The gas transfers angular momentum to the neutron star, gradually increasing its rotation rate. Over time, an older pulsar that had slowed down can be spun up again, until each rotation takes only a few milliseconds. The companion may eventually become a white dwarf, lose most of its material, or disappear through a more disruptive interaction. PSR B1257+12 is isolated today in the sense that it has no stellar companion, but its rapid spin suggests a history that may once have involved one. The same missing companion may also be connected to the material from which the planets formed, although the exact sequence of events is still debated. Rotation by itself does not create the pulses we detect. A neutron star appears as a pulsar when beams of electromagnetic radiation sweep across our line of sight. Its magnetic axis is not necessarily aligned with its rotation axis. Charged particles move through the powerful magnetic environment, and radiation is produced in concentrated regions associated with the magnetic poles. As the neutron star turns, those beams move through space. Whenever a beam crosses Earth, a telescope records a pulse. The star is not repeatedly switching itself on and off. The beam is pointing toward us, then away from us, and then toward us again. This is why the lighthouse comparison is useful. A lighthouse lamp does not vanish between flashes. Its beam rotates, and an observer sees the light only when it passes in their direction. PSR B1257+12 behaves in the same general way. except the rotating object is a neutron star and the full sweep happens more than 100 times every second. No coastal authority would approve it for practical navigation. Ships would find the flashing somewhat excessive, and the surrounding high-energy radiation would create additional paperwork. The phrase, listening to radio waves, also needs a small adjustment. Radio waves are not sound waves. They do not travel through space as pressure changes that a human ear could hear. A radio telescope collects electromagnetic radiation with a large dish and a receiver. Electronics convert the incoming signal into data that can be recorded and analysed. Astronomers can later transform those data into audible sounds for demonstrations, but the pulsar itself is not making a noise in the ordinary sense. Space remains silent to unaided ears. The listening happens through instruments, computers, timing standards, and a great deal of patient correction. At Arecibo Observatory, the main collecting surface was a 305-metre dish built into a natural depression in Puerto Rico. It gathered weak radio signals over a large area and directed them toward receivers suspended above the dish. PSR B1257+12 was discovered there, and regular timing observations began in 1990. The telescope could not see the pulsar as a visible object with a clear surface and colour. It recorded the repeating radio signal, allowing astronomers to determine how often the pulses arrived and whether that schedule changed. An individual pulse is not always identical to the pulse before it. Its strength and exact shape may vary, and radio interference from Earth can complicate the observation. Astronomers therefore combine many rotations to produce a stable average pulse profile. With PSR B1257+12, there is no shortage of rotations. A single minute contains close to 10,000 turns of the star. The recorded pulses can be aligned and added together, making the repeated shape clearer while random variations become less important. That average shape becomes a template. A new observation is compared with the template, and the amount by which the observed profile must be shifted gives a precise time of arrival. The method does not depend on someone watching a screen and pressing a button when a line appears. The timing is calculated by comparing detailed signal profiles. A template is built by averaging many recorded profiles, providing a stable reference against which later observations can be matched. Each arrival time measurement includes information about the telescope, the observing frequency, the clock reference, and the uncertainty of the result. A long sequence of these measurements allows astronomers to create a timing model. That model predicts when the pulses should arrive after accounting for the pulsar's rotation, its position in the sky, its gradual slowdown, the motion of Earth, and the known effects of the material through which the signal has travelled. The observed arrival times are then compared with the prediction. Earth's movement must be included because the telescope is not sitting still. Our planet rotates, so the observatory moves around Earth's axis. Earth also travels around the Sun, changing its distance from the pulsar during the year. For precise timing, astronomers convert measurements to a common reference linked to the solar system's centre of mass, known as the barycenter. Otherwise, the ordinary motion of Earth would create delays that could be mistaken for something happening around the pulsar. It would be unfortunate to announce a new planet only to discover that the supposed orbit was Puerto Rico travelling around the Sun as usual. The radio signal also passes through the interstellar medium before reaching us. Space between the stars is extremely thin, but it is not completely empty. Free electrons in that material affect radio waves in a frequency-dependent way. Higher radio frequencies arrive slightly earlier than lower frequencies, spreading the pulse across the observing band. This effect is called dispersion. Astronomers measure and correct the delay so that the different frequencies can be brought back into alignment and the pulse can be timed more accurately. Dispersion provides useful information of its own. The amount of delay indicates how many free electrons the signal has encountered along its route, which can help estimate a pulsar's distance. The estimate depends on models of how electrons are distributed through the galaxy, so it is not the same as placing a measuring tape between Earth and the pulsar. Changes in the interstellar medium can also alter the delay over time. Modern precision observations often use several radio frequency bands so that variations caused by interstellar material can be separated from changes produced by the pulsar, its planets, or the observing equipment. Clock corrections matter as well. A radio telescope needs a stable time reference because the entire method depends on knowing exactly when the signal arrived. Instrumental delays, receiver changes, calibration errors, updates to time standards, and the position of the solar system's barycenter all need to be considered. Pulsar timing may sound like a person placing a stopwatch beside a telescope, but it is closer to maintaining a detailed account in which every known delay must be entered correctly. After the corrections are applied, the measured times are compared with the model's predictions. The differences are known as timing residuals. If the model is accurate and nothing significant has been left out, the residuals should be small and should not form an organized pattern. There will still be measurement noise, but the point should not repeatedly rise and fall, according to a clear schedule. A persistent pattern means that the model is missing something. Several possible causes have to be considered. The pulsar's position may be slightly wrong in the model. Its rotation rate or slowdown may need adjustment. The interstellar medium may have changed. The observatory clock may require another correction. A companion may be pulling the pulsar back and forth. The residual does not arrive with a helpful note saying, "This delay was produced by a planet." It simply tells astronomers that the current explanation does not account for everything. For PSR B1257+12, the remaining variations contain strong repeating components with periods of about 66.6 days and 98.2 days. Alexander Fulstian and Dale Frail interpreted these patterns as the effects of planet-sized companions. The signals behaved as though the pulsar was moving around shared centres of mass with two orbiting bodies. The original 1992 announcement reported companions in almost circular orbits at distances broadly comparable with the inner region of our own solar system. The basic reasoning is the same one used when studying many binary systems. A planet orbits a pulsar, but the pulsar is not completely stationary. Both objects move around their shared centre of mass. Since the pulsar contains nearly all the mass, its movement is small, while the planet completes the much larger orbit. Small does not mean irrelevant. The radio pulses travel across space at the speed of light, so even a slight change in the pulsar's position changes how long they take to reach Earth. When the pulsar moves a little closer to us, the pulses have a shorter distance to travel and arrive earlier than predicted. When it moves a little farther away, they travel an extra distance and arrive later. The pattern repeats with the companion's orbit. By measuring the period and size of the delay, astronomers can infer the period of the orbit and place limits on the companion's mass. The planet itself remains unseen, but its gravitational effect is written into the travel time of the radio signal. The pulsar therefore serves as both the central object and part of the measuring system. Many exoplanet searches monitor ordinary starlight. A transit causes a slight drop in brightness when a planet crosses the star. Radial velocity measurements detect changes in the star's spectrum as it moves toward and away from Earth. Around Lich, the useful quantity is the arrival time of the radio pulses. The planets move the source of those pulses through space, producing a schedule of early and late arrivals. Imagine placing a very steady clock on a trolley and slowly rolling it backward and forward along a long corridor. Someone listening from the far end would not receive each tick at exactly the interval expected. When the clock moved closer, the signal would arrive sooner. When it moved away, the signal would arrive later. The clock's own rhythm might remain steady throughout. The change would come from the distance travelled by the signal. Lich behaves according to a much more demanding version of that simple idea. Calling a pulsar a perfect clock would go too far. Pulsars gradually lose rotational energy, so their rotation slows. Some experience sudden changes called glitches. Their pulse shapes can vary, and changes in the magnetosphere or interstellar medium can introduce noise. Even the best millisecond pulsars require detailed models and repeated observation. Their value comes from their predictability, not from literal perfection. Once the gradual slowdown and other known behaviour are included, the remaining differences can be measured with remarkable accuracy. For suitable millisecond pulsars, modern timing programs can achieve residuals below a microsecond. Pulsars have become tools for studying binary companions, testing theories of gravity, examining the interstellar medium, checking time standards, and searching for very low-frequency gravitational waves. A rotating stellar remnant can therefore operate as a detector for events taking place far beyond its immediate system. PSR B1257+12 offered an especially useful combination. It rotated rapidly, produced measurable radio pulses, and could be observed repeatedly with Arecibo. The variations were not isolated irregularities that appeared at random. They returned according to organized periods. A model containing 2 Keplerian orbits provided an excellent match to the pulse arrival times, reducing the unexplained residuals to only a few microseconds in early analyses. Any alternative explanation would need to imitate planetary orbits with comparable precision over many repeated cycles. That was persuasive, but astronomers also wanted a test that did not rely only on fitting 2 separate orbital patterns. The 2 larger planets, now called Poltergeist and Phobetor, have periods close to a 3:2 ratio. Because their orbits are comparatively close and their masses are several times that of Earth, they should pull on one another. Their paths should not behave as 2 completely independent ellipses. Each planet's gravity should cause small changes in the other's orbit. Researchers predicted the timing effects that these interactions would produce. Continued observations later detected the expected perturbations. This confirmed that the signals were produced by bodies with planetary masses interacting through gravity. The mutual perturbations also allowed better estimates of the planet's true masses and orbital inclinations, showing that the 2 larger orbits are close to the same plane. Draugr produced a much smaller signal because its mass is far lower. Its orbit lasts about 25.3 days, and its gravitational pull causes a weaker displacement of the pulsar. Recognizing that signal required careful analysis of what remained after the larger effects and standard timing behavior had been modeled. The same natural clock that revealed 2 Earth-mass worlds made it possible to identify a companion with only about 2% of Earth's mass. Around an ordinary star, an object this light would be extremely difficult to find with many traditional methods. It would block very little starlight during a transit, assuming its orbit even passed across the star from our viewpoint. Its gravitational pull would create a small radial velocity signal. Beside a well-timed millisecond pulsar, however, its mass could be recognized through repeated changes in the radio signal's arrival schedule. This method explains why Draugr's orbit is known far better than its appearance. A repeating timing pattern reveals an orbital period. Its shape gives information about eccentricity and orbital phase. Its amplitude constrains the planet's mass, although the result may depend on the inclination of the orbital plane. None of those measurements requires reflected light from the planet. The same timing pattern does not automatically reveal the planet's colour, surface material, atmosphere, weather, or exact radius. It tells us how the object moves and how strongly it pulls on the pulsar. It does not tell us what a stone would look like on its surface, or whether anything resembling a sky exists above it. Draugr is gravitationally obvious and visually unknown. The lighthouse image can also become misleading when carried too far. It may suggest that a narrow visible beam sweeps over each planet, leaving the system dark between flashes. Pulsars can produce radiation across several parts of the electromagnetic spectrum, along with streams of energetic particles. The radio beam crossing Earth is the part we can time with exceptional precision. It is not a complete description of every form of energy surrounding Lich or reaching its planets. At approximately 161 rotations per second, Lich completes nearly 14 million turns during one Earth day. During one of Draugr's short years, the pulsar rotates hundreds of millions of times. The planet's orbit is therefore measured against an enormous number of stellar rotations. Astronomers do not need to examine each turn separately, but their model must keep track of the accumulated pulse phase across long periods of observation. Losing count would damage the timing solution, rather like trying to measure a month with a clock that occasionally forgets whether it is Tuesday. The regularity comes partly from the neutron star's enormous rotational inertia. A household clock can be disturbed by a weak battery, a temperature change, or someone knocking it from a table. A neutron star is more difficult to inconvenience. Its rotation still evolves, but that evolution can often be modelled. Once the expected change is removed, smaller deviations become useful evidence. This is why millisecond pulsars are sometimes described as natural clocks placed throughout the galaxy. They were not installed for our benefit, and each has its own complications. Even so, a group of well-timed pulsars can reveal effects that influence radio travel times across enormous distances. PSR B1257+12 became famous for its planets, while timing arrays built from other pulsars are being used to study disturbances associated with gravitational waves. The scientific target changes, but the central task remains familiar: predict the arrival, measure the arrival, and investigate the difference. For someone listening at home, the calculations can make the process feel remote. The basic logic is less unfamiliar than it first appears. A repeated signal changes because its source is moving. A regular clock seems to run early or late because the distance between the clock and the observer is changing. Pulsar timing adds precise clocks, radio frequency corrections, orbital mathematics, interstellar plasma, and decades of observations, but it still depends on noticing that repeated signals carry information about motion. The discovery did not begin with an image of 3 planets arranged around a glowing remnant. It began with timestamps. Rows of pulse arrival times were compared with a model, and the differences refused to behave randomly. They traced repeating schedules. Those schedules matched orbital motion. The interactions of the 2 larger companions then supplied an additional test. What looks obvious in an artist's illustration first appeared in scientific data as a clock that would not keep the expected time. That description makes Litch sound defective, though the opposite is closer to the truth. The clock was precise enough to reveal why the pulses were arriving early and late. An irregular pulsar might have hidden the planets inside noise. A stable pulsar exposed them. The apparent fault belonged not to the clock, but to the assumption that it was standing still. Once the pulsar's movement was included, the timing pattern became a map of unseen orbits. The roughly 66-day rhythm belonged to one planet. The 98-day rhythm belonged to another. A weaker 25-day signal pointed toward Draugr. Each companion added its own small delay to radio pulses crossing the distance to Earth. Astronomers separated those overlapping patterns in much the same way that several notes can be identified within a chord, although this particular chord arrived as columns of numbers and required considerably more software. Draugr did not block enough light to create an obvious transit, and there was no ordinary stellar spectrum to examine for the small back-and-forth shift used in many exoplanet searches. The planet contributed no useful image of its own. What astronomers had instead was a radio signal arriving from PSR B1257+12, along with the knowledge that the signal was not reaching Earth at precisely the times predicted by a simple model of an isolated pulsar. To understand how a planet can be found this way, it helps to separate the pulse from the planet. Draugr does not create the radio pulses. Those come from the rapidly rotating neutron star. The planet's role is gravitational. As Draugr moves through its orbit, it pulls on the pulsar. The pull is extremely weak compared with the gravity of the neutron star, but no orbiting body leaves its host completely motionless. The planet and pulsar both travel around a shared centre of mass. Because Litch contains nearly all the mass in the pair, its orbit around that common point is very small. Draugr makes the large circuit, while the pulsar performs a tiny wobble. The same thing happens in the solar system. We usually say that Earth orbits the Sun, which is accurate enough for most conversations and considerably easier than interrupting breakfast to discuss barycenters. More precisely, Earth and the Sun move around their shared centre of mass. Since the Sun is much more massive, that point lies very close to the Sun's centre. Jupiter pulls the Sun more strongly and causes a larger movement, but even Earth prevents it from remaining perfectly fixed. Stars with planets are therefore always moving to some degree in response to their companions. With an ordinary star, astronomers may detect that movement by measuring changes in the star's spectrum. When the star moves toward Earth, its spectral lines shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. This is the radial velocity method, and it has revealed many exoplanets. A pulsar provides another option. Rather than measuring a shift in ordinary starlight, astronomers measure a change in the travel time of repeated radio pulses. Suppose the pulsar moves a little closer to Earth during one part of Draugr's orbit. The radio signal then has a slightly shorter distance to cross, so the pulse reaches the telescope earlier than expected. Half an orbit later, the pulsar has been pulled slightly farther away. The next pulses must cross a little more space and arrive late. This early and late pattern repeats every time the planet completes an orbit. The period of the pattern reveals the length of the planet's year. Its amplitude gives information about the size of the pulsar's movement, and therefore the gravitational influence of the unseen companion. The distances involved in that wobble are small by astronomical standards, but radio waves travel at a known speed, and millisecond pulsars offer a large number of repeated signals. If the source moves by only a modest distance along our line of sight, the resulting travel time difference may be measured in microseconds or milliseconds. That sounds inconveniently small, until we remember that Lich rotates roughly 161 times every second. Astronomers are not waiting several months for the next useful tick. They receive thousands of rotations during a short observation and can combine many pulses to build a stable average profile. An individual pulse may be noisy. Its strength can vary. Interference from Earth can contaminate the observation, and the signal has travelled through interstellar material before entering the receiver. Instead of relying on a single flash, astronomers collect a sequence of pulses and add them together according to the known rotation period. Random variations begin to average out, while the repeating pulse shape becomes clearer. The resulting profile can then be compared with a high-quality reference template. The comparison produces a time of arrival, usually shortened to TOA in technical discussions. The term sounds as though astronomers are waiting at an airport gate, but it refers to the measured arrival time of a selected point in the average pulse profile. Software determines how far the observed profile must be shifted to align with the template. That shift can be translated into a precise timestamp, together with an uncertainty showing how reliable the measurement is. One timestamp is not enough to reveal a planet. A timing program may continue for months or years, collecting arrival times at different dates, and sometimes at different radio frequencies. Each measurement becomes one part of a much larger model. The model includes the pulsar's rotation rate, its gradual slowdown, its position in the sky, the motion of Earth, the behaviour of the observatory clock, and the effects of the material between the pulsar and the telescope. Only after these known influences are handled can a repeating planetary signal become convincing. Earth's motion creates some of the largest corrections. A telescope on Earth is carried around the planet's axis once per day. It is also carried around the Sun once per year. The distance between the telescope and PSR B1257+12 therefore changes constantly. If astronomers used the raw arrival time recorded at the observatory, the movement of Earth would introduce delays much larger than the signal from Draugr. The measurements are converted to a reference frame associated with the solar system's barycenter, allowing observations taken at different points in Earth's orbit to be compared consistently. The calculation requires an accurate position for the pulsar. If its sky coordinates are slightly wrong, the correction for Earth's orbit will also be slightly wrong, producing an annual pattern in the timing residuals. A position error can therefore imitate organised behaviour. Astronomers fit the pulsar's coordinates along with other parameters and check whether the remaining pattern persists. The method is sensitive enough that an incorrect assumption about where the source lies can leave a signature in the data. The radio signal also encounters free electrons in the thin material between the stars. Those electrons delay lower radio frequencies more than higher ones, spreading the pulse as it crosses the observing band. This is called dispersion. The effect is predictable and can be measured, but the amount of material along the path may vary over time. Observations at multiple frequencies help astronomers distinguish a delay caused by interstellar plasma from one caused by the motion of the pulsar around a planetary system. Instrumental delays need attention as well. Signals pass through receivers, cables, filters, and electronic systems before becoming stored data. Equipment can be replaced or recalibrated. Time standards can be updated. A tiny, unnoticed offset between observing systems could appear as a jump in the pulse arrival times. Precision timing therefore involves records of the instruments and clocks used during each observation. Discovering a planet is exciting, but discovering that someone changed a cable 3 months earlier is a less satisfying explanation and must be considered first. Once the known corrections have been applied, astronomers compare the measured arrival times with the times predicted by the model. The differences are called timing residuals. If the pulsar behaves exactly as modelled, the residuals should be scattered around zero without a large repeating shape. A pulse may arrive a little early or late because of measurement uncertainty, but the deviation should not rise and fall according to a regular period. When a repeating pattern remains, the model is missing something. That missing element might be an error in the pulsar's rotation rate, a change in the interstellar medium, an instrumental problem, or an effect intrinsic to the pulsar. It might also be orbital motion. A companion produces a particularly recognizable signature because the delay repeats according to the geometry of an orbit. A nearly circular orbit creates a smooth, roughly sinusoidal timing variation. The pulses become progressively earlier as the pulsar moves toward us, return toward the predicted schedule as it crosses the middle of its small orbit, become progressively later as it moves away, and then return again. An eccentric orbit produces a less symmetrical pattern because the orbital speed changes. The timing model can fit parameters such as the orbital period, eccentricity, orientation, and projected size of the pulsar's movement. In the first analysis of PSR B1257+12, precise observations made with the 305-meter Arecibo radio telescope revealed strong periodic timing variations. Vulsjan and Frail reported two principal periods of about 66.6 and 98.2 days. The most straightforward model involved two planet-sized bodies moving in nearly circular orbits around the 6.2 millisecond pulsar. Their initial minimum mass estimates were several times the mass of Earth. The 1992 paper also noted evidence that at least one additional planet might be present. The word minimum matters because timing initially measures the part of the pulsar's motion directed along our line of sight. If a planetary orbit is tilted relative to us, we do not observe the full three-dimensional movement. The inferred mass is therefore commonly written with a factor involving the orbital inclination. A companion viewed nearly edge-on produces a large line of sight effect for its mass. One viewed closer to face-on would need to be more massive to create the same measured signal. For the larger planets, that uncertainty was later reduced by measuring how they affected one another. Draugr is too small to produce equally useful interactions, so its mass depends more heavily on the assumed or inferred geometry of the system. Modern catalogue values place it near 0.02 Earth masses, with an orbital period of approximately 25.26 days, and an orbital distance of about 0.19 astronomical units. The tiny inner signal was more difficult than the two large patterns. Draugr moves the pulsar by a much smaller amount, so its timing signature lies closer to the level where modelling errors and other sources of variation become important. Astronomers had to account for the larger planets, the pulsar's rotational behaviour, Earth's motion, dispersion, and the remaining technical corrections before the roughly 25-day pattern could be interpreted as another orbiting body. This explains why the two larger worlds were announced first in 1992, while Draugr's discovery date is generally listed as 1994. The small planet did not suddenly appear in that year. Its effect had been present in the observations. It took a longer timing record and a more complete analysis to separate the weak signal from everything around it. The 1994 confirmation paper reported the moon mass inner object, along with the measured gravitational interaction of the two larger planets. A periodic signal alone deserves caution. Pulsars are useful clocks, but they are physical objects rather than manufactured devices. Their rotation can contain irregularities. Their magnetic environments can change, and those changes may affect both the shape and timing of the radio pulses. Modern searchers have found that quasi-periodic magnetospheric activity can sometimes imitate the signal expected from a planetary companion. A convincing detection must therefore do more than locate a neat wave in the residuals. Astronomers look for consistency across time, observing frequency, pulse shape, and different ways of modelling noise. The location of PSR B1257+12 near the ecliptic also created a specific concern about the small planet. In 1997, researchers suggested that the 25.3-day timing signal might be connected to effects in the heliosphere associated with solar rotation, rather than to an orbiting body. The proposed explanation noted that the signal was small and that radio waves from the pulsar travel through the solar environment before reaching Earth. That suggestion is useful because it demonstrates how discoveries are tested. An accepted catalogue entry does not become immune to alternative explanations. Researchers examine whether an effect produced nearer to Earth could generate the same period, whether the signal changes with radio frequency, and whether it remains consistent when the timing model and data improve. Draugr continues to be listed as a confirmed planet in the NASA Exoplanet Archive and NASA's Exoplanet Catalogue, but the earlier challenge shows why a microsecond-scale signal cannot simply be labelled planetary without detailed scrutiny. The two larger planets offered a much stronger confirmation test. Their orbital periods are close to a ratio of 3:2. While the inner of the pair completes about 3 orbits, the outer completes roughly 2. Because the planets have several Earth masses and travel on relatively nearby paths, their gravity causes measurable changes in one another's orbital motion. These perturbations were predicted shortly after the original announcement. If the timing patterns truly came from 2 planets, the residuals should gradually depart from a model that treated the orbits as completely independent. The prediction was unusually valuable. Many suppose planetary signals can be fitted by an orbit, but a fitted orbit is still an interpretation. Here, the planetary model made an additional forecast about future timing behaviour. The 2 companions should exchange small amounts of orbital energy and angular momentum. Their orbital periods, eccentricities, and phases should change in a specific way. Those changes would then shift the arrival times of the pulsar's radio pulses by measurable amounts. After 3 years of systematic timing observations with Arecibo, the expected gravitational perturbations were detected. The result confirmed that the periodic signals came from interacting planetary mass bodies. It also confirmed the first planetary system known outside the solar system. The evidence did not depend merely on 2 independent repeating curves. The curves were changing because the unseen companions were pulling on one another in the way real planets should. That test is similar to noticing 2 pendulums affecting each other through a shared support. Either pendulum might be described by a regular period on its own, but a detailed measurement would reveal a small exchange between them. If the predicted exchange appears, it confirms that both objects are physically present and interacting, rather than being 2 unrelated errors in the measurement. Later timing analyses used these interactions to estimate the true masses and orbital inclinations of Poltergeist and Phobetor. Assuming a neutron star mass of 1.4 suns, the values were found to be about 4.3 and 3.9 Earth masses, with orbital inclinations suggesting that the two paths are nearly coplanar. The microsecond variations caused by their mutual gravity provided information that ordinary independent orbital fits could not supply. Draugr could not be confirmed through a comparable mutual interaction because its gravity is much weaker. The larger worlds outweigh it by roughly 200 times. Their effect on one another rises above the timing noise. Draugr's effect on them is far harder to isolate. Its case rests on the repeatability and fit of its own timing signal, the quality of the overall model, and the continued consistency of observations. The scale of the wobble can be approached through a simple calculation. The planet and pulsar balance around their shared centre of mass. Draugr's orbital radius is about 0.19 astronomical units, while its mass is only a tiny fraction of the assumed 1.4 solar mass pulsar. Multiplying the orbital size by that mass ratio gives the approximate size of the pulsar's own small orbit around the barycenter. Because the planet is so light, the pulsar's displacement is measured in only kilometres rather than in a substantial fraction of an astronomical unit. A few kilometres is negligible beside the distance between stars, but the corresponding light travel time can still reach several microseconds. Radio waves cover about 300 metres in 1 microsecond. If the pulsar moves along our line of sight by a kilometre, the arrival time changes by a little more than 3 microseconds. The exact observed amplitude depends on inclination and the fitted orbital parameters, but the comparison shows how a city-sized movement at the source can become a measurable delay at Earth. This does not mean the telescope measures the pulsar's position with a ruler accurate to a few kilometres across hundreds of parsecs. It measures time, and the known speed of light connects that timing difference to distance. A radio pulse that repeatedly arrives several microseconds early and late provides evidence that its source is moving through a corresponding projected distance. The inference is precise because the pattern repeats through many orbits. Draugr completes one orbit in a little over 25 days. During that time, Lich rotates hundreds of millions of times. Astronomers can collect many observing sessions across repeated planetary orbits and ask whether the weak pattern keeps the same period and phase. A random disturbance should not remain organised indefinitely. A planet should return to the same orbital position according to a predictable schedule, apart from any small long-term interactions. The process resembles detecting a slow vibration in an extremely fast machine. The pulsar provides rapid ticks. The planet introduces a much slower cycle into their arrival times. Several cycles overlap because 3 planets are moving the pulsar at once. The timing model separates the roughly 25-day, 66-day, and 98-day components, while also fitting the neutron star's rotation and the motion of Earth. None of the planets is observed separately, yet each contributes a distinct schedule. A useful analogy is to imagine 3 people gently pulling a wheeled chair from different directions using long elastic cords. The person sitting in the chair is tapping a spoon against a cup at a perfectly regular rate. A listener far away cannot see the chair or the people, but the tapping reaches them slightly early or late as the chair moves. 2 people pull strongly and slowly. The third pulls much more weakly but completes the cycle faster. With enough measurements, the listener could separate the 3 repeating motions without seeing any of them. The analogy has limits. Orbits are governed by gravity rather than elastic cords. The pulsar rotates instead of tapping a spoon, and any real attempt involving several people, a chair, and precision timing would probably end with someone asking why the corridor is blocked. It does, however, preserve the main point. The planet is detected through movement transferred to a source that emits a repeated signal. The phrase, "heard a planet," is therefore a convenient description rather than a literal one. Astronomers did not receive radio broadcasts from Draugr. They did not hear wind, impacts, or activity on its surface. The pulsar supplied the radio waves. Draugr altered their arrival times by shifting the pulsar's position. What was heard was the effect of gravity on a clock. This distinction is important because planets are sometimes discussed as though every detection provides the same information. A transit can estimate a planet's radius. Radial velocity provides a mass constraint. Direct imaging may reveal light from the planet. Pulsar timing is especially sensitive to orbital motion and companion mass, but it may tell us almost nothing about the body's surface. Each method reveals a different part of an object that remains mostly inaccessible. For Draugr, timing gives a secure rhythm. It tells us that the body completes an orbit in about 25.3 days and moves close to the pulsar compared with its larger companions. It provides the gravitational evidence used to estimate its very low mass. It does not tell us whether the planet has craters, metal plains, frozen material, or an atmosphere. The method detects the invisible world as a dynamical participant rather than as a visible place. The discovery also depended on the decision to keep observing. Early data can suggest a period, but a longer baseline shows whether the pattern repeats and whether alternative explanations remain viable. Every additional orbit gives the model another opportunity to fail. If the predicted early pulse arrives late, or the signal drifts away from the expected phase, the planetary interpretation weakens. If the pattern continues, confidence grows. Long observations are especially important when several effects share similar timescales. Earth's orbit creates annual behavior. The Sun rotates in roughly a month, influencing the solar wind through which the radio signal may pass. Instrument schedules and seasonal observing conditions can also introduce patterns. A 25-day signal must be separated from these possibilities, which is why measurement at several frequencies and careful modelling of the solar system environment are valuable. There is no single moment when a faint line on a screen suddenly turned into Draugr. The planet emerged through repeated measurements, improved models, and the removal of more ordinary explanations. First, the strong signals revealed a system. Then interactions between the larger planets confirmed that the orbital interpretation was physically correct. Within the remaining timing structure, a much weaker cycle pointed to the small inner body. The invisible world became credible because its gravity kept repeating the same small instruction to the pulsar. Move this way, then that way, and begin again. Once a repeating wobble has been separated from the noise, the next question sounds simple. How heavy is the object causing it? With Draugr, that question becomes slightly awkward, because nobody can collect the planet, place it on a scale, and ask it to remain still while the reading settles. Astronomers are trying to weigh something they cannot see, located roughly 2,000 light-years away, using delays in radio pulses that may last only a few millionths of a second. It is not the most convenient arrangement, but astronomy has rarely been organised for convenience. The word weight is also not quite correct. Weight is the force caused by gravity acting on an object, which changes depending on where the object is placed. A person weighs less on the Moon than on Earth while retaining the same mass. Astronomers are interested in Draugr's mass, meaning the amount of matter it contains and the strength of its gravitational influence. There is no universal bathroom scale involved, which is probably fortunate. A planet on a bathroom scale would create several problems before anyone reached the part where they wrote down the number. The starting point is the tiny orbit made by the pulsar. Draugr travels around Lich, but Lich also moves because Draugr pulls on it. The two bodies balance around a common centre of mass. The position of that balance point depends on the mass of each object and the distance separating them. A heavy companion moves the pulsar more, a light companion moves it less. By measuring the pulsar's motion and the length of the orbit, astronomers can estimate the mass responsible for the wobble. This does not require knowing what the planet is made of. Iron, rock, ice, and other materials can all produce the same gravitational pull if the total mass is the same. The timing observations therefore weigh Draugr without revealing whether its interior resembles Mercury, the Moon, Pluto, or something formed from a mixture rarely found in our own planetary system. Gravity supplies the amount. composition must wait for information that is much harder to obtain. Draugr's timing signal gives it an orbital period of about 25.26 days. Its orbit lies at approximately 0.19 astronomical units from the pulsar, and the current catalogue mass is about 0.020 Earth masses, with an uncertainty of roughly 0.002 Earth masses. The value is based on the timing solution, and an adopted orbital inclination of about 50 degrees. An earlier result was often expressed as a minimum mass of approximately 0.015 Earth masses, because the exact tilt of the orbit was not yet known. Orbital inclination is important because the telescope does not observe the pulsar's full movement in 3 dimensions. It measures the part directed toward and away from Earth. Imagine watching someone walk in a circle. If the circle is seen from the side, the person appears to move clearly from left to right and back again. If it is seen almost from above, much of the motion is hidden in the plane of the view. The same orbit can therefore produce different measured signals depending on its angle. For a single unseen companion, timing often gives a quantity involving the planet's mass multiplied by the sine of the inclination. This is why early results are described as minimum masses. If an orbit is viewed edge-on, the sine of the inclination is close to 1, and the minimum mass is close to the true mass. If the orbit is more face-on, the true mass must be larger to create the same measured motion along our line of sight. The observation tells us that the planet cannot be lighter than a certain amount, but it may initially leave room for it to be heavier. In the case of Draugr, astronomers could use the broader geometry of the system to choose a likely inclination. The orbits of the 2 larger planets have been measured through their gravitational interactions, and they are nearly coplanar. The inner planet is generally modelled as belonging to the same flattened system, rather than moving on a completely unrelated angle. With an inclination near 50 degrees, Draugr's estimated true mass becomes about 2% of Earth's mass. 2% sounds almost like nothing when it is presented as a percentage. It is not nothing. Earth has a mass of nearly 6 trillion kilograms. 2% of that is roughly 120 sextillion kilograms, depending on the exact mass estimate used. Draugr contains more matter than the Moon, although it is still far lighter than Mercury. It is also around 9 times more massive than Pluto. Calling it almost massless is therefore acceptable only when the comparison is with full-sized planets. Compared with any object that might fit inside a house, Draugr remains unnecessarily substantial. The Moon has about 1.2% of Earth's mass, so Draugr's catalogue mass would place it at roughly 1.5 to 2 lunar masses. Mercury has about 5.5% of Earth's mass, making Draugr a little over 1/3 as massive as the smallest major planet in our solar system. These comparisons put it into an unusual range. It is lighter than every official planet orbiting the Sun, but heavier than the dwarf planets and most moons that people commonly recognise. Its radius has not been directly measured. NASA lists an estimated radius of 0.338 Earth radii and classifies Draugr as terrestrial, but that figure is based on a mass-radius relationship rather than a transit or a resolved image. A planet rich in iron could be smaller and denser. A body containing more low-density material could be larger. Without a direct radius, astronomers cannot calculate an exact density or surface gravity. This is an important limit. Mass is not the same as size. A ball of lead and a ball of foam can have equal mass while occupying very different volumes. Planets follow more complicated rules because their own gravity compresses their interiors, but the same principle remains. Draugr's gravitational effect tells us how much mass is present. It does not tell us exactly how widely that mass is distributed. If the estimated radius is reasonably close, Draugr would be a rounded world several thousand kilometres across. It might be comparable in width to a large moon, though its mass would make it denser than some icy moons. Any statement about its surface gravity must remain provisional, because both radius and composition are uncertain. A visitor would not drift away as though the planet had forgotten to switch on gravity. but no responsible travel company could yet print an accurate baggage allowance. The measurement becomes more reliable when the entire planetary system is considered rather than Draugr alone. Lich has 3 confirmed companions. Draugr is the small inner planet. Poltergeist, officially PSR B1257+12 C, moves farther out with an orbital period of about 66.54 days, an orbital distance of roughly 0.36 astronomical units, and a mass of about 4.3 Earths. Phobetor, PSR B1257+12 D, takes approximately 98.21 days to orbit at around 0.46 astronomical units, and has a mass of about 3.9 Earths. The contrast is enormous. Poltergeist is more than 200 times as massive as Draugr. Phobetor is nearly 200 times as massive. If the 3 planets were placed on one side of an old-fashioned balance scale, Draugr would contribute very little to the total. This does not make it unimportant. It makes its detection more impressive and its formation more puzzling. Poltergeist and Phobetor are commonly described as super-Earths, because each is several times the mass of Earth while remaining far below the mass of Neptune. Their radii are estimated rather than directly measured, just as Draugr's is, so the term refers mainly to their mass range. Super-Earth does not mean a better Earth, a larger habitable world, or a planet with improved customer service. It is a broad category that tells us very little about the surface conditions. The names of the family were officially approved as part of the International Astronomical Union's Name Exoworlds program. Lich refers to a fictional undead creature. Draugr comes from undead beings in Norse mythology. Poltergeist is a German term for a noisy ghost associated with physical disturbances. Phobetor is a figure from Greek mythology connected with nightmares. The naming theme was based on undead creatures and supernatural beings of the night. The names are unusually appropriate, but they arrived long after the scientific designations. Early research called the planets A, B and C ordered outward from the pulsar. Under the exoplanet naming system now used in major catalogues, the inner planet is lowercase b, the middle planet is C, and the outer planet is D. This creates the mildly irritating situation in which the object once called Planet A is now Planet B, while the former planets B and C have become C and D. Anyone who finds this confusing has understood the situation correctly. The system's historical importance lies mostly with the 2 larger worlds. In 1992, Alexander Wolszczan and Dale Frail reported periodic timing variations indicating at least 2 planet-sized companions around the 6.2 millisecond pulsar. Their initial minimum mass estimates were 3.4 and 2.8 Earth masses, and their orbital periods were approximately 66.6 and 98.2 days. These became the first confirmed exoplanets, although later measurements refined their true masses upward to the values used today. That sequence sometimes causes confusion, because another exoplanet, 51 Pegasi b, is often remembered as the first. It was the first planet found orbiting a sun-like star, and the discovery that brought exoplanets into much wider public attention. The pulsar planets came earlier. The first confirmed planetary family outside our solar system was therefore not arranged around a normal star. It circled a neutron star left after a stellar catastrophe. This was a strange beginning for the study of exoplanets. Astronomers had spent centuries wondering whether ordinary stars possessed ordinary planetary systems. When reliable evidence finally arrived, it pointed to planets beside an object that had already passed through one of the most violent stages of stellar evolution. Instead of finding another Jupiter around another sun, researchers found several low-mass worlds around a pulsar rotating every few milliseconds. The original timing signals gave minimum masses, but Poltergeist and Phobetor offered astronomers a way to go further. Their orbital periods are close to a 3-to-2 relationship. For roughly every 2 orbits completed by Phobetor, Poltergeist completes about 3. The planets are not in a simple, exact resonance, but the near commensurability allows their gravity to produce measurable, repeating disturbances in each other's orbital motion. These disturbances were predicted soon after the discovery. If the two timing patterns came from real planets, their mutual gravitational pull should gradually modify the pulse arrival times in a specific way. The orbital periods, eccentricities, and positions would not remain perfectly independent. Detecting those changes would provide a test of the planetary explanation, and would reveal information about masses and inclinations that the original signals could not provide alone. Continued observations found the predicted perturbations. The two invisible bodies behaved as planets with several Earth masses should behave. They pulled on the pulsar, but they also pulled on one another. This gave astronomers something close to a controlled experiment carried out by the system itself. The planets produced an orbital pattern. The theory predicted how that pattern should change, and later measurements detected the change. The confirmation mattered because pulsar timing had already suffered one famous false alarm. A proposed planet around another pulsar, PSR B1257+12 A, was withdrawn after an error involving Earth's orbit was identified. That mistake encouraged understandable caution. A repeating timing signal could not be trusted merely because it looked planetary. The PSR B1257+12 system was stronger because the two large companions applied a separate dynamical test. Their mutual effects could not easily be explained by a misplaced coordinate or an overlooked calendar correction. By analysing microsecond variations created by the interaction, Messier Konaki and Alexander Volschan estimated the true masses of Poltergeist and Phobetor at about 4.3 and 3.9 Earth masses. They found orbital inclinations of approximately 53 and 47 degrees, depending on which equivalent orientation is used. The closeness of those angles showed that the planets travel in nearly the same plane. Coplanar orbits are common in planetary systems formed from disks. The planets around the Sun move in roughly the same plane because they formed from a flattened disk of gas and dust. The alignment of Poltergeist and Phobetor suggests that they also emerge through an organised formation process, rather than being captured independently from random directions. Their near 3-to-2 period relationship adds to the impression of a system shaped by interactions within a disk. Draugr does not contribute enough gravity for its interactions to be measured with comparable precision. Its mass is so small that its influence on the two super-Earths is difficult to separate from the rest of the timing data. The inclination used for Draugr is therefore linked to one of the system solutions rather than established through a strong direct perturbation measurement of its own. The catalogue value of 0.020 Earth masses is more informative than the original minimum estimate, but it is still built on the assumption that the inner orbit fits the family's overall geometry. That assumption is reasonable, though not identical to seeing the orbit. A planet formed in the same disk would be expected to travel in approximately the same plane as its siblings. A captured object might arrive at a sharply different angle, but independent capture of several small planets into stable, orderly orbits around a pulsar would require an unlikely sequence of events. The simplest explanation is that the three worlds share a common origin, or at least a closely connected history. The measured masses also help test the long-term stability of the system. Computer integrations using the refined orbital values indicate that the known arrangement can remain stable over very long periods. Poltergeist and Phobetor do not quickly collide or eject one another, and Draugr's low mass means it has little power to disrupt the outer pair. The planets occupy a broad, stable region, although their motion includes subtle, resonant and secular effects. This stability tells us that the family is not a brief accident that happens to be visible just before it falls apart. The current configuration can persist, allowing the timing patterns to remain coherent across decades of observation. It also places constraints on possible additional planets. A large unseen companion in the wrong orbit could disturb the system or introduce timing signals that have not been observed. There have been suggestions of other bodies around Lich, including possible distant companions, asteroid belts, or debris. None has reached the same secure status as the three confirmed planets. A planetary system can contain material too small or too distant to produce an obvious timing signature, but scientific catalogues must separate possibilities from confirmed objects. For now, the recognised family contains Draugr, Poltergeist and Phobetor. The family arrangement becomes easier to grasp if it is compared with the inner solar system. Draugr orbits at 0.19 astronomical units, closer to Lich than Mercury is to the Sun. Poltergeist travels at about 0.36 astronomical units, near the scale of Mercury's average distance. Phobetor lies at approximately 0.46 astronomical units, still well inside Earth's orbit. If the whole system were placed around the Sun, all three confirmed worlds would fit within the inner half of Earth's orbital path. Their years are correspondingly short. Draugr needs about 25 days, Poltergeist about 67, and Phobetor about 98. The outer planet of this family completes a year only a little more slowly than Mercury does. The arrangement is compact, but not so compact that the planets constantly pass near one another. Their orbital spacing and low eccentricities help maintain stability. Draugr's orbit is listed with an eccentricity of 0 in the current archive solution, meaning it is treated as essentially circular. Poltergeist and Phobetor have small eccentricities, around 0.019 and 0.026 in the earlier fitted solutions. Their paths are therefore only slightly stretched rather than resembling narrow ellipses. This orderly geometry supports the idea that the planets formed through a disk that reduced large differences in orbital direction and shape. The three masses make the family especially unusual. There is no Jupiter-sized planet dominating the system. There is no known Neptune equivalent. Two members are super-Earths, while the inner planet is smaller than Mercury and only modestly more massive than the Moon. This is not a scaled copy of our solar system. Its architecture appears to have been assembled under different conditions and possibly from a much smaller supply of material. The difference between Draugr and its siblings may preserve clues about the disk in which they formed. In many disks, temperature and material distribution change with distance from the central object. The inner region may contain less solid material, or may expose forming planets to stronger radiation and particle winds. Small bodies can also be lost through collisions, migration or evaporation. Draugr may be a remnant of an inner population that never grew as large as the outer planets. Alternatively, it might once have contained more material and lost some of it. A pulsar can expose nearby bodies to high-energy radiation and particle bombardment. A low-mass planet would have difficulty holding a thick atmosphere, and volatile surface material could be removed over time. This does not mean that a large rocky planet can simply be reduced to any desired size, but erosion and atmospheric loss may influence what remains. NASA describes the three planets as being subjected to intense radiation from the pulsar. The mass measurement alone cannot tell us whether Draugr began small or became smaller. It only describes the planet's present gravitational effect. To reconstruct its history, astronomers must combine the masses, orbital spacing, inclinations, eccentricities, age estimates, pulsar properties, and models of possible formation disks. Each piece limits the number of stories that remain plausible. A planet formed before the neutron star's creation would have faced the mass loss and shock of a supernova. A planet formed afterward would require a new disk of material around the remnant. A planet created during the recycling of the pulsar might come from matter transferred by a companion star. The shared plane of the larger planet strongly favours some kind of disk formation, but several events could have supplied that disk. This is where weighing the planets becomes more than an exercise in assigning numbers. The masses tell us how much material the disk had to provide. The low eccentricities tell us that the orbits were probably settled rather than violently scattered. The inclinations show that at least the two larger planets share a common plane. Their near 3-to-2 relationship records a history of orbital interaction. Draugr's very low mass shows that the same process produced, preserved, or reshaped an object far smaller than its neighbours. The family also demonstrates why a planet does not need to resemble Earth to change astronomy. Poltergeist and Phobetor were the first confirmed exoplanets, and Draugr extended the discovery to an exceptionally low mass. Together, they proved that planets could exist around a stellar remnant, and that pulsar timing could detect bodies ranging from several Earth masses down to something near the scale of a large moon. Their names make them sound like members of a haunted household, but their behaviour is governed by ordinary gravity. Poltergeist does not move objects without touching them. It moves Lich and Phobetor through gravitational attraction. Phobetor does not cause nightmares, though standing on it without radiation protection would be a poor decision. Draugr has not risen from a grave in the literal sense. It is a planet orbiting a stellar remnant, and the language of ghosts gives us a memorable way to label a system whose real history is already strange enough. Draugr's low mass is not a sign that it barely exists. Its gravity shifts a neutron star by enough for radio telescopes to detect the change from across the galaxy. That is a useful reminder of how sensitive the timing method can be. A planet only a little heavier than the Moon can leave a measurable pattern in signals that have travelled for thousands of years. The mass also changes how we imagine its short orbit. Draugr does not race around Lich because it is light. A heavier planet placed at the same distance would have nearly the same orbital period, because the neutron star dominates the system's mass. The family's masses explain how strongly each planet pulls on Lich, but they do not immediately tell us what it would mean to travel around that object. Draugr completes the journey in about 25.262 Earth days. That is its year, the time required to return to the same position in its orbit around the pulsar. While Earth needs a little more than 365 days to make one circuit of the Sun, Draugr finishes more than 14 years during the same interval. Anyone attempting to maintain an Earth-style birthday tradition there would require a large supply of candles and a relaxed attitude toward aging. The short year comes mainly from Draugr's distance from Lich and the mass of the pulsar. The planet travels at an average distance of about 0.19 astronomical units, or 19% of the average distance between Earth and the Sun. Its orbit would fit well inside Mercury's if the two systems could somehow be placed on top of each other. Mercury circles the Sun at an average distance of about 0.39 astronomical units and needs 88 Earth days to complete a year. Draugr is closer to its central object, and Lich is assumed to contain about 1.4 times the mass of the Sun, so Draugr must move quickly to remain in orbit. Using the catalogue distance and orbital period, a nearly circular orbit would give Draugr an average speed of roughly 82 km per second. Earth moves around the Sun at about 30 km per second, so Draugr travels almost 3 times faster. It would cross the distance between London and New York in a little over a minute, although there are no cities on its known surface, no aircraft, and no one waiting at the other end with luggage. The comparison merely gives human scale to a speed that otherwise arrives as another large number. The orbit is listed as essentially circular. That means Draugr does not spend part of its year falling very close to Lich and another part moving far away. Its distance remains comparatively steady as it travels around the system. A perfectly circular orbit is usually a mathematical simplification, and the real path may contain an eccentricity too small for the available data to establish clearly. But it is reasonable to describe Draugr's route as close to circular. This makes one Draugr year very regular. The planet follows almost the same path at almost the same distance, and returns after a little more than 25 days. There would be no long winter caused by the planet moving far from the pulsar, followed by a short period of intense heating near the closest point. Any seasonal changes would have to come from something else. Perhaps the tilt of the planet's rotational axis, changes in how radiation reaches the surface, or interactions between an atmosphere and the planet's rotation. None of those properties has been measured. The word year may also create the wrong mental picture. On Earth, a year is connected to seasons, birthdays, school calendars, tax deadlines, and an annual attempt to remember where the decorations were stored. On Draugr, it is simply an orbital period. There is no evidence of seasons, weather, biological cycles, or anyone complaining that the year seems to pass more quickly each time. The 25-day figure describes motion, not experience. We do not know the length of a day on Draugr. An orbital period tells us how long the planet takes to travel around Lich, while a rotation period tells us how long it takes to spin once around its own axis. Earth's year is about 365 days, because Earth rotates hundreds of times during one orbit. Mercury rotates only about 1.5 times during each of its years, creating a relationship between its day and orbit that is very different from ours. Draugr's rotation has not been measured, so it could turn rapidly, slowly, or in a pattern influenced by tides from the neutron star. Tidal locking is a reasonable possibility because Draugr is close to a massive central object. Gravitational forces can gradually alter a planet's spin, reducing the difference between its rotation period and its orbital period. A fully locked planet would keep roughly the same side facing Lich throughout its orbit, as the Moon keeps nearly the same side facing Earth. However, whether Draugr is locked depends on its age, internal structure, original rotation, orbital history, and how efficiently its interior responds to tidal forces. None of these is known well enough to state that one hemisphere permanently faces the pulsar. Even if it were locked, the result would not resemble the familiar day side and night side of a planet orbiting an ordinary star. Lich does not illuminate its surroundings like the Sun. The neutron star is extremely small, emits radiation across several energy ranges, and drives a relativistic pulsar wind. The amount of usable visible light on Draugr is uncertain. A hemisphere facing the pulsar would be exposed to the central object's energetic output, but it might not sit beneath a bright circular sun producing ordinary daylight. From Draugr, the physical body of the neutron star would appear tiny. A neutron star is roughly city-sized, while the planet remains tens of millions of kilometers away. The Sun appears broad in our sky because it is nearly 1.4 million kilometers across. Lich may contain more mass than the Sun, but that mass is compressed into a diameter of only a few tens of kilometers. Mass determines the orbit. Visible width depends on size and distance. Draugr therefore circles an object with enormous gravitational importance and a very small apparent disk. If visible radiation from Lich was strong enough for human eyes to detect, it would be concentrated into a point rather than spread across a large solar face. The sky would not necessarily brighten in the smooth way Earth's sky does at sunrise. Any atmosphere could scatter incoming radiation, but there is no confirmed atmosphere. Without one, the sky would remain dark even while the ground was exposed to radiation, much as the lunar sky remains black when the Sun is above the horizon. The rotating radio beam adds another complication. We see Lich as a pulsar because its beam sweeps across Earth. That does not mean Draugr is struck by the same narrow radio beam during every rotation. The planet's orbital plane and the geometry of the magnetic beam are not known well enough to describe exactly how often the beam crosses the planet. It could pass across parts of the orbit, miss the planet entirely, or illuminate it in a pattern that changes as Draugr travels. The radio pulses detected on Earth describe our viewing angle, not a universal flashing experienced equally in every direction. Radio emission is also only a small part of the local environment. The pulsar loses rotational energy, producing a wind made of highly energetic particles and electromagnetic fields. X-ray observations with the Chandra telescope have detected faint emission from PSR B1257+12. The measured X-ray luminosity is low compared with that of many other millisecond pulsars, but the planets are close enough that the radiation and particle wind may still be important to their atmospheres and surfaces. A study of neutron star planets examined whether X-rays and pulsar winds could heat atmospheres, and whether those atmospheres might survive. The outcome depends strongly on how effectively the incoming energy is absorbed and converted into heat. A thick atmosphere could thermalize some high-energy radiation, spreading energy through the gas rather than allowing it to strike the surface directly. A thin atmosphere might offer little protection, and could be removed over time. The properties of pulsar winds are uncertain enough that estimates for surface conditions cover a wide range. Those studies focused mainly on the two larger planets because stronger gravity would make it easier for them to retain dense atmospheres. Draugr is much smaller. With only about 2% of Earth's mass, it would have a weaker hold on atmospheric gas, especially if its radius is near the modelled estimate. Energetic radiation can heat gas until particles escape, while the pulsar wind can help strip material away. This makes a substantial long-lived atmosphere less likely, although no direct observation has confirmed that Draugr is completely airless. Without an atmosphere, temperature becomes difficult to describe with one useful number. A surface exposed to incoming energy can become much warmer than a surface turned away from it. Rock stores and conducts some heat, and the rate of rotation influences how long each region is exposed. If the planet rotates quickly, heating may be shared across much of the surface. If it is tidally locked and lacks an atmosphere, the side facing the main energy source could remain warmer, while the opposite side radiates heat into space. Yet the pulsar's output is not equivalent to sunlight. X-rays and relativistic particles deposit energy differently from visible and infrared radiation. Some may interact with the upper atmosphere if one exists. Some may create showers of secondary particles. Some may reach solid material and alter its chemistry. The surface temperature would depend not merely on how much energy arrives, but on what form it takes and how the planet absorbs, reflects, conducts, and re-emits it. This is why calling Draugr either frozen or scorched can be misleading. It may contain regions that are very cold and others that receive substantial energetic bombardment. Its thermal state could change with depth. A surface can be cold in the ordinary sense while still being exposed to radiation that would damage biological tissue and alter minerals. Temperature measures the average motion of particles in matter. Radiation hazard measures how energetic incoming particles and photons interact with that matter. The two are related, but they are not interchangeable. One trip around Lich lasts 2,182,636.8 seconds. During that interval, the pulsar completes roughly 351 million rotations, based on its measured period of about 6.2185 milliseconds. The exact total changes slightly as the neutron star gradually slows, but the comparison gives the scale. Draugr does not orbit a lighthouse that flashes a few times each night. It travels around an object completing hundreds of millions of turns during every local year. If the planet were crossed by one of the emission beams on each pulsar rotation, the flashes would occur far too rapidly for human eyes to distinguish. More than 100 pulses per second would blend into what seemed like a continuous source, much as individual frames in a film merge into motion. Instruments could separate the pulses. Human senses would experience only the average effect, assuming a person could somehow stand there with the necessary protection and the exceptionally questionable travel insurance. The distance between Draugr and Lich also introduces a small but interesting delay. At 0.19 astronomical units, light or radio waves would take roughly 95 seconds to travel from the pulsar to the planet. When Lich changes, Draugr cannot respond immediately. Information about the change reaches the planet a little more than a minute and a half later. Earth receives sunlight about 8 minutes after it leaves the sun, so this delay is shorter, but it remains significant enough to remind us that even one planetary system is not experienced all at once. The value follows from the catalogue orbital distance and the travel time of light across one astronomical unit. Gravity also propagates at the speed of light according to general relativity, though stable orbital calculations do not require imagining Draugr chasing old information about where the pulsar used to be. The gravitational field and the motion of the system form a consistent relativistic structure. For ordinary descriptions, it is enough to say that Draugr follows a stable orbit determined by Lich's mass and the system's existing motion. The neutron star's mass allows Draugr to orbit quickly without falling inward. Orbital motion is a continual fall that keeps missing the central object. Gravity pulls the planet toward Lich, while Draugr's sideways velocity carries it forward. The combination produces a curved path. If the planet lost enough speed, its orbit would shrink. If it gained enough, it would move into a wider orbit or escape. At roughly 82 kilometers per second, it moves at the speed appropriate for its present distance around a neutron star of the assumed mass. This speed does not create a constant wind over the surface because space itself offers almost no ordinary resistance. Earth travels around the Sun at nearly 30 kilometers per second, yet we do not feel a planetary headwind from the orbit. An atmosphere travels with its planet, and the near vacuum around a world does not behave like air around a moving car. Draugr's orbital speed matters for its trajectory and energy, not for whether loose objects are blown from the ground. The pulsar wind is different. It consists of particles and fields flowing outward from Lich, and a planet moving through that environment may form a complicated interaction region. If Draugr possesses a magnetic field, it could deflect some charged particles and create a magnetosphere. The boundary would be shaped by pressure from the pulsar wind on one side, and the planet's magnetic field on the other. Earth has a related interaction with the solar wind, though the conditions near Lich would involve different particle energies and a much more exotic central source. No magnetic field has been measured for Draugr. Small rocky bodies can preserve internal magnetic fields if their interiors contain moving conductive material, but the field may weaken as the interior cools. The planet's origin could also influence its iron content and internal heat. If Draugr formed from unusual stellar debris, its interior might differ substantially from those of familiar rocky planets. Any image of a glowing aurora over the surface therefore remains speculative. Its neighbours would also have a place in the sky. Poltergeist orbits at about 0.36 astronomical units, while Phobetor travels near 0.46 astronomical units. Their positions relative to Draugr would change as all three planets moved at different speeds. Poltergeist needs about 66.5 days to complete an orbit, and Phobetor needs about 98.2 days. Draugr repeatedly overtakes both of them, producing changing configurations in which the planets appear on the same side of Lich, opposite sides, or somewhere between. Whether either neighbouring planet would appear as more than a point depends on its radius and its distance from Draugr at the time. Their actual radii have not been directly measured, and the gaps between the orbits remain millions of kilometres wide. They would not hang in the sky like an enormous moon. At favourable alignments, they might be detectable as bright or dark points if they reflected or emitted enough energy. But the system offers no confirmed observations from which to describe their appearance. The planets do not line up every Draugr year. Each has its own orbital period, so the relative arrangement changes from one 25-day circuit to the next. Draugr may return to the same position around Lich, while Poltergeist and Phobetor remain elsewhere in their longer orbits. A full repetition of the family's geometry would require a much longer interval, and would never be perfectly exact because the larger planets perturb each other. Those interactions are strongest between Poltergeist and Phobetor. Draugr is too light to shift their paths very much, but it is not entirely disconnected. Every mass in the system contributes to the gravitational field. In a complete dynamical model, the planets and pulsar all respond to one another. Draugr's contribution is simply small enough that the system can often be described without focusing on its effect on the larger pair. The planet's orbit is stable on the timescales covered by observation and modelling. It has completed hundreds of revolutions since the first timing data revealed it, and the signal remains associated with the same short period. Long-term numerical studies of the system find that the low masses and present arrangement support stability. This does not mean the orbit will remain unchanged forever. Gravitational interactions, the pulsar's loss of rotational energy, and rare external disturbances can alter systems over immense periods. It means there is no evidence that Draugr is about to fall into Lich or be thrown into interstellar space. The year itself would not be marked by obvious changes in the pulsar's physical appearance. Lich is too small and distant from Draugr for the planet's movement along a near-circular orbit to make it visibly swell and shrink. The direction of the radio beam or pulsar wind relative to the planet might change through the orbit, but we do not know the geometry well enough to identify a local season of stronger or weaker exposure. If Draugr has a significant axial tilt, different regions could face the incoming energy at different angles during the orbit. On Earth, the seasons result mainly from axial tilt, not from changes in distance from the Sun. A tilted Draugr might have a similar geometric cycle, but its unknown rotation and unusual radiation environment would make the consequences very different. There is no measurement of its axial tilt, so assigning it a summer and winter would be an exercise in world building rather than astronomy. A local calendar could still divide the orbit into useful sections. One might mark the times when Draugr, Poltergeist and Phobator form certain alignments, or when the planet passes through regions of different pulsar wind intensity. Without observers, these divisions remain imaginary, but the orbit itself provides a reliable repeating unit. Every 25.262 days, the gravitational timing signature returns through the same phase. That reliability is exactly why astronomers can detect the planet. The short period provides many repeated cycles during a few years of observation. A planet with an orbit lasting several centuries would produce only a small part of its timing pattern during a human research career, making the signal much harder to interpret. Draugr's rapid year allows astronomers to watch the pulse delays rise and fall again and again. Short orbits also help establish whether a signal remains coherent. A false pattern caused by changing interstellar material, equipment, or pulsar activity may drift in strength or phase. An orbiting planet should maintain a predictable schedule. Draugr has completed thousands of revolutions since the radio signal began its journey toward modern telescopes, and dozens of its years passed during a modest span of Earth-based observations. The orbit does not tell us how the planet reached its current position. It may have formed near 0.19 astronomical units from Lich, or it may have migrated through a disk after forming elsewhere. Young planets exchange angular momentum with surrounding gas and solid material, allowing their orbital distances to change. Collisions and gravitational interactions can also shift orbits. The nearly circular path may indicate that a disk damped earlier irregularities, but the present orbit is the final page available to us, not a complete record of every movement that came before. Its closeness to Lich may also have influenced what material could condense during formation. A hot young disk would prevent some volatile substances from remaining solid near the centre, while metals and rocky minerals could condense at higher temperatures. The pulsar and any accretion activity may have heated the disk differently from the young sun's protoplanetary disk. If Draugr formed after the neutron star already existed, its ingredients were selected under conditions unlike those that built Earth. The 25-day route therefore connects orbital mechanics to composition. The planet's position controls its speed and exposure. Its exposure affects which gases and surface materials might survive. The formation temperature at that distance may have influenced which solids were available. Its low mass affects how easily it can retain an atmosphere, while any tidal heating depends on the orbit, spin, and interior. What looks like a simple calendar number begins to place limits on the physical world travelling through that calendar. Draugr completes its circuit without giving us a photograph. Lich rotates hundreds of millions of times. The two larger planets advance through their slower paths. Radio pulses leave the system, cross interstellar space, and eventually arrive at telescopes on Earth with the timing changes that reveal where the small planet has been. Each 25-day cycle repeats the measurement, but it also keeps the planet's surface hidden. To move beyond the orbit, we have to ask what kind of object can contain about 2% of Earth's mass, remain in a tight path around a pulsar, and endure the conditions of that system for a very long time. The material completing that 25-day orbit is much harder to measure than the orbit itself. Astronomers can follow Draugr's gravity with impressive precision. They can determine how often it circles the pulsar, estimate its distance from the centre of the system, and calculate that it contains about 2% of Earth's mass. None of those measurements reveals what would be beneath your feet if standing on the planet were possible. Timing data tell us that matter is present. They do not provide a list of ingredients. There is no direct image of Draugr. The planet has not been observed passing across a bright stellar surface, so its radius has not been measured through a transit. Its reflected light has not been separated from the system, and no spectrum has revealed minerals, gases, or clouds. NASA lists an estimated radius of about 0.338 times that of Earth and classifies the planet as terrestrial, but the radius comes from a model connecting planetary mass with likely size. It is not the result of seeing the edge of the world. That distinction leaves several possible compositions open. Draugr might be made mainly of silicate rock, broadly resembling the solid material found in Earth's mantle, the Moon, Mars, and many asteroids. It could contain a large iron-rich core. It might have formed from carbon and oxygen released by a disrupted white dwarf. It could contain material processed inside an earlier star, producing ratios of elements that differ from those in the planets around the Sun. Some volatile substances may once have been present and later removed. The planet could even contain layers created under conditions with no close equivalent in our own system. The safest starting point is ordinary rocky material. Planets with masses below Earth's are commonly expected to contain mixtures of metal and silicate if they form from a disk with broadly familiar chemistry. Iron and nickel tend to collect toward the centre, while lighter rocky minerals remain above them. Heat from collisions, radioactive elements, and gravitational compression can melt a young planetary body, allowing dense material to sink and less dense material to rise. This process, known as differentiation, produced Earth's metallic core and rocky mantle. Draugr may have experienced the same basic process. Even a body only modestly heavier than the Moon can generate enough early heat to separate internally, especially if it formed rapidly through energetic collisions. A young Draugr might have begun partly or extensively molten. Iron could have moved inward, leaving a rocky mantle and crust above it. The surface would then have cooled while the deeper interior retained heat for longer. That description sounds familiar because it is based on the formation of rocky objects in our solar system. The problem is that Draugr may not have formed from familiar starting material. The disk around Lich was almost certainly created during an unusual sequence of stellar events. The two larger planets have nearly coplanar orbits and a close orbital relationship, strongly supporting formation within a flattened disk rather than independent capture. The disk existed, but its source remains uncertain. A planet's composition begins with the composition of its disk. The disk that formed Earth contained material inherited from the cloud that produced the Sun. Hydrogen and helium dominated the original gas, while smaller quantities of oxygen, carbon, silicon, magnesium, iron, and other elements supplied the solids. Temperature determined where different substances could condense. Metals and rocky minerals could solidify close to the young Sun. Water ice and other volatile compounds survived more easily farther out. The disk around Lich may have followed very different rules. It could have formed from material that fell back after the explosion that created the neutron star. It might have come from a companion star losing gas to the pulsar. It may have resulted from the destruction of that companion. A proposed model even involves the merger of a neutron star with a carbon and oxygen white dwarf, producing a disk unusually rich in those two elements. Each possibility gives Draugr a different chemical starting point. Consider the simplest rocky possibility first. If the disk contained a mixture broadly comparable to ordinary planet-forming material, Draugr could be a smaller version of a terrestrial planet. Its interior might include an iron core surrounded by silicate rock. The exact fraction of metal would affect its radius. A metal-rich planet is denser and smaller than a planet of equal mass made mostly of silicates. A planet containing substantial low-density material would be larger. Since Draugr's radius is not directly known, astronomers cannot use density to choose between these options. Density is calculated by dividing mass by volume. The mass estimate is available, but the volume depends on the radius. Using an estimated radius to calculate density would mostly return the assumptions built into the radius model. It would look like a measurement while quietly being a calculation based on another calculation, which is a reliable way to produce a very tidy answer to a question that remains open. The nearby pulsar may have removed much of the lighter material from the planet. Draugr has relatively weak gravity compared with Earth, and it has spent a long time close to a source of energetic radiation and particles. Gas in an atmosphere can absorb high-energy radiation, become hot, and escape. A pulsar wind can also interact with the upper atmosphere and carry material away. A small world would have more difficulty replacing that loss through volcanic activity or retaining light gases over billions of years. For this reason, an airless rocky object may be the most straightforward picture. Its surface could consist of heavily altered minerals exposed directly to radiation and particle bombardment. Micrometeorite impacts might gradually grind the upper layers into loose material, producing something comparable to the regolith covering the Moon. The comparison should not be pushed too far. The intensity and type of radiation around Lich differ greatly from the environment near Earth, and Draugr's surface chemistry may be unfamiliar. Energetic particles can damage crystal structures, knock atoms from the surface, and create new compounds through radiation-driven reactions. Some atoms may be ejected into space through sputtering, a process in which incoming particles strike a surface and remove material. Others may be implanted into the ground. Over very long periods, the exposed crust could become chemically and physically different from the fresh rock below it. The planet's colour would depend on that composition and alteration. Iron-rich minerals can appear dark, red or brown under ordinary light. Carbon-rich material can be extremely dark. Fresh silicate rock can range through greys, whites, greens, and darker shades. Radiation may darken some surfaces while bright impacts expose less altered material beneath them. Without reflected light measurements, selecting one colour would be no more scientific than choosing curtains for a room that has never been entered. A metal-rich Draugr is another possibility. Planet formation can produce unusually dense objects if collisions remove much of the rocky mantle, while leaving the metallic core behind. Mercury may have an unusually large core relative to its size, though the reason remains debated. In a compact and energetic pulsar system, early impacts could have been severe enough to strip outer layers from some forming bodies. Draugr might therefore be the remnant of a larger object that lost material through collisions. This would help explain its low mass while allowing it to retain a dense interior. However, there is no direct evidence for such a specific history. The orbit is nearly circular, which suggests that strong irregularities were eventually reduced, perhaps through interactions with a disk. A violent collision could have occurred early and been followed by orbital settling, but the current timing data do not record the event. If Draugr were rich in iron, its actual radius would probably be smaller than a silicate planet of the same mass. Surface gravity would then be somewhat stronger than expected for a more weakly compressed, larger object. The surface might contain metallic material mixed with rock, although a pure exposed iron world would be an extreme case. Even planets with large cores generally retain some mantle, unless major impacts remove it. A carbon-rich origin offers a more unusual picture. White dwarfs are the compact remnants of stars that were not massive enough to become neutron stars. Many contain cores dominated by carbon and oxygen. If a carbon-oxygen white dwarf approached a neutron star closely enough, tidal forces could disrupt it. Its material could spread into a disk around the neutron star. Part of that disk might accrete onto the neutron star, spinning it up, while material farther out cooled and formed solid bodies. A 2016 model proposed this kind of neutron star and white dwarf merger as an explanation for the PSR B1257+12 planets. In the model, the disrupted white dwarf creates a carbon and oxygen-rich disk. Under suitable conditions, enough solid material remains at planetary distances to form the observed worlds. The authors suggested that such planets could be carbon-rich and might contain interiors with large quantities of crystalline carbon, including diamond. The word diamond tends to take over the conversation at this point. It creates an image of Draugr as a giant gemstone circling a pulsar, which is memorable and may also be misleading. A carbon-rich planet would not necessarily resemble a polished jewel. Diamond is one possible form of carbon under high pressure. A planet containing large amounts of it could still have a dark, rough surface covered by graphite, carbon compounds, impact debris, and other minerals. Most of the diamond could lie deep inside, where pressure supports the crystalline structure. A carbon-rich interior would also not make the planet financially useful. Value depends partly on scarcity and access. Transporting planetary quantities of diamond from a system hundreds of parsecs away would require technology considerably beyond a jewelry shop's usual supply chain. The planet would also remain beside a pulsar and would not respond well to a standard mining license. The white dwarf disruption model is attractive because it may explain several features at once. It provides a disk containing enough heavy elements to form planets, offers a way to spin up the neutron star, and naturally creates unusual chemistry. The low occurrence of pulsar planetary systems may fit a rare merger event. It also avoids requiring ordinary planets to survive the original supernova unchanged. Attractive does not mean confirmed. Other formation calculations have explored disks produced by fallback material after a supernova or by mass transfer from a stellar companion. Simulations of terrestrial planet assembly show that several disk models can produce planets with roughly the observed masses and eccentricities, although reproducing the compact arrangement of PSR B1257+12 is difficult. Some studies found that a disk with a more solar-like composition could match aspects of the system better than one made almost entirely from heavy elements. This disagreement is not a failure of the science. The planets preserve only part of their formation history. Their masses and orbits provide constraints, but several earlier sequences can lead to similar final arrangements. Researchers must begin with different possible disks, simulate how material spreads and cools, allow solid particles to settle, form planetary embryos, model collisions, and compare the outcome with the observed system. A successful result shows that a scenario is possible. It does not always prove that nature selected it. A fallback disk would form from material that failed to escape after the supernova. Some of the star's ejected matter could lose energy and return toward the neutron star, settling into an orbiting disk. The material would have been processed inside a massive star so it could contain substantial quantities of heavy elements. Dust and solid particles might eventually condense, collide, and grow into planets. The challenge is angular momentum. Material falling back close to the neutron star may not spread far enough to place large amounts of matter at the current planetary distances. The disk must move mass outward, while other material moves inward. Models differ over whether enough solid matter could reach the region where Draugr, Poltergeist, and Phobator formed. The white dwarf disruption model was partly developed because a disrupted companion can naturally provide a disk with more angular momentum. Another family of ideas begins with a pulsar in a binary system. Millisecond pulsars are generally thought to be spun up by taking material from a companion star. Gas transferred from the companion forms an accretion disk, and some of that gas may remain available for planet formation. Alternatively, radiation from the pulsar may evaporate or disrupt the companion, producing material that settles into a circumpulsar disk. Models proposed soon after the planet's discovery showed that planetary formation could occur during or after such a phase. If the material came from the outer layers of an ordinary low-mass star, the disk might contain a composition closer to the material that formed familiar rocky planets. Draugr could then be silicate-rich rather than carbon-dominated. If the companion had already evolved into a white dwarf, the disk might be much richer in carbon and oxygen. The unknown identity and fate of the former companion therefore sit at the centre of the composition question. The system's high speed through the galaxy adds another clue, though it does not settle the matter. Very long baseline interferometry measured a transverse velocity of about 326 km per second and a distance of roughly 710 parsecs. The high motion suggests that the pulsar experienced a substantial kick during its history, possibly during the supernova that formed it. Researchers reviewing the formation scenarios concluded that the planetary disk most likely arose from the evaporation or disruption of a former binary companion. Even with a likely disk source, Draugr may not share exactly the same composition as its larger siblings. Conditions change with distance from the centre of a disk. Draugr formed or settled nearer to Lich than Poltergeist and Phobator. The inner disk would generally be hotter. Materials that could remain solid farther out may have stayed gaseous near Draugr's orbit. The planet may therefore contain a greater proportion of substances that condense at high temperatures, including metals and refractory minerals. Disk material also migrates. Small solid grains drift through gas. Planetary embryos exchange angular momentum with the disk and may move inward or outward. Collisions mix bodies formed at different distances. Draugr's current position does not guarantee that every part of it condensed at 0.19 astronomical units. It may contain material transported from warmer or cooler regions. Its very low mass could record a shortage of solids in the inner disk. Perhaps most of the available matter accumulated farther out, where Poltergeist and Phobator became several Earth mass planets. Draugr may have formed in a region containing less material and stopped growing when the disk dispersed. It may also have migrated inward after its growth ended. Another possibility is that larger embryos formed close to Lich, but collided or fell into the pulsar, leaving Draugr as the remaining small body. Planet formation is not an orderly process in which every grain is assigned to the nearest planet. Growing objects disturb one another's orbits, merge, scatter, and sometimes disappear into the central star. Draugr's mass could represent what remained after a much busier early period. The present surface may reveal almost nothing of the original disk. Billions of years of radiation, impacts, internal cooling, and possible volcanism could have altered the upper layers. If the planet once had water, carbon dioxide, methane, or other volatile compounds, much of that material may have escaped. If it possessed a molten surface early in its history, minerals may have separated according to density and melting point. Later impacts could have mixed the crust again. A small planet cools faster than a large one because it has more surface area relative to its volume. Draugr may therefore have lost much of its internal heat earlier than Earth did. Its volcanic activity could have declined long ago. A frozen interior is not guaranteed, especially if radioactive elements or tidal effects provide continuing energy, but the planet probably has less capacity than Earth to maintain a long-lived active mantle. Tidal heating depends on orbital eccentricity and internal flexing. Draugr's orbit is treated as nearly circular, so strong tidal heating like that experienced by Jupiter's moon Io is not an obvious expectation. If the orbit contains a small eccentricity, or if interactions once made it more elongated, tides may have contributed more heat in the past. The current timing solution does not support a picture of Draugr being continually kneaded by extreme orbital changes. The planet might still contain a metallic core capable of producing a magnetic field, but no such field has been detected. A magnetic dynamo usually requires electrically conducting fluid moving inside a rotating body. If Draugr's core cooled and solidified, any global field may have weakened. If its interior remains partly liquid, a field might persist. The answer depends on composition, heat flow, rotation, and age, nearly all of which remain uncertain. A magnetic field would not reveal the composition by itself, though it could provide clues about a conductive interior. It might also reduce the direct impact of some charged particles from the pulsar wind. High-energy photons such as X-rays would not be stopped in the same way. Even a magnetized Draugr would remain in a severe radiation environment. There is little reason to expect a thick layer of ordinary water ice at the surface. The planet orbits close to Lich, and its small mass makes atmospheric and volatile retention difficult. Yet it would be premature to declare that no water molecules exist anywhere inside it. Water can be locked within minerals, trapped below a crust, or delivered by impacts. The composition of the original disk may have included oxygen and hydrogen in some form. The main uncertainty is not whether a few water molecules could exist, but whether enough survive to create a significant layer or reservoir. The same caution applies to an atmosphere. A thin collection of atoms released from the surface could surround the planet temporarily, forming an exosphere rather than a dense atmosphere. Impact, sputtering, or radioactive decay could continually supply particles while radiation removes them. Mercury and the Moon possess extremely thin exospheres, even though neither has an Earth-like atmosphere. Draugr may have something comparable, but no observation has detected it. At present, the most accurate description is not rock planet, iron planet, or diamond planet. It is a very low-mass planetary body whose composition has not been measured directly. A rocky and metallic structure is plausible. A carbon-rich interior is possible under a white dwarf disruption model. A more ordinary silicate composition remains possible under other disk scenarios. Extensive surface volatiles and a thick atmosphere appear more difficult to retain, but they have not been observationally ruled out in every form. That may feel less satisfying than a clear answer. We are accustomed to labels that make worlds easy to picture. Earth is blue and rocky. Jupiter is a gas giant. Neptune is an ice giant. Even those descriptions hide enormous complexity, and they are based on spacecraft observations, spectra, gravity measurements, magnetic fields, and decades of study. Draugr has provided us mainly with a gravitational signature. Expecting a detailed mineral inventory from that signature would be like determining the contents of a sealed parcel by watching how strongly it bends a shelf. The uncertainty is also useful. Each possible composition points back toward a different history. A silicate and iron Draugr might have formed from a disk with relatively familiar chemistry. A carbon-rich Draugr would support a connection to a disrupted white dwarf. An unusually metal-dense planet might preserve evidence of high-temperature condensation or violent collisions. Remaining volatiles would place limits on radiation exposure, atmospheric loss, and the planet's original supply of material. The material available to build Draugr depends on when the planet appeared. If it existed before the neutron star formed, then it began life around an ordinary star and somehow survived that star's destruction. If it appeared later, its ingredients came from matter that collected around the neutron star after the explosion, perhaps from falling supernova debris, or from a companion star that was stripped apart. These possibilities lead to very different planets, even if they produce the same mass and orbit today. At first, survival may seem like the simpler answer. Stars commonly form with disks, and disks commonly produce planets. The massive star that eventually became Lich could have possessed a planetary system long before its core collapsed. Draugr, Poltergeist, and Phobator might then be the remaining members of that original family. They would be first-generation planets, older than the neutron star and present during the explosion that created it. This version avoids having to build planets in the unusual environment around a pulsar. It allows the worlds to form through the same broad process that made Earth: dust settling in a disk, grains sticking together, planetesimals colliding, and larger bodies gradually taking shape. The difficulty comes later, when the host star ages. A star massive enough to leave a neutron star does not move quietly from ordinary life into retirement. As its nuclear fuel changes, the star expands and loses material. Its outer layers may reach far beyond their earlier boundaries. Planets close to the star can be engulfed, heated, stripped, or dragged inward. Worlds farther away may survive the expansion, but their orbits change as the star loses mass. By the time the core collapses, the original system may already look very different from the orderly disk in which it formed. Reviews of post-main sequence systems show that planets around neutron star progenitors must pass through several destructive stages even before the supernova itself is considered. The supernova then creates a second and more immediate problem. A large amount of stellar material is expelled over a short time. The gravitational mass holding the planets in their old orbits suddenly decreases, and the newly formed neutron star may receive a kick because the explosion is not perfectly symmetrical. A planet that had been travelling at the correct speed around the original star can find itself moving too quickly for the weaker gravitational field that remains. Its orbit may become highly elongated, or the planet may escape completely. Survival is possible under certain conditions. A sufficiently distant planet may avoid being physically destroyed, and an explosion that removes the right amount of mass in a favourable direction can leave it bound. The problem is not that every pre-existing planet must disappear. The problem is explaining how 3 surviving planets would end up in the particular configuration observed around Lich. Draugr, Poltergeist and Phobetor occupy compact, almost circular orbits. The 2 larger planets move in nearly the same plane, and their periods lie close to a 3:2 relationship. Those features look like the results of formation and adjustment within a disk. They do not look like 3 unrelated survivors that pass through rapid mass loss and a strong stellar kick while keeping neat, closely aligned paths. Analyses of the system have therefore regarded a purely pre-supernova origin as facing serious objections and have favoured formation after the neutron star was created. Distance creates another difficulty for the survival idea. A planet close enough to occupy Draugr's present orbit would have been deep inside the region, affected by the expansion of the progenitor star. Draugr now travels only about 0.19 astronomical units from Lich. A massive star near the end of its life can expand far beyond that distance. The present planets might have moved inward later, but that would require a disk or another mechanism capable of rearranging their orbits after the explosion. Once such a disk is introduced, it becomes reasonable to ask whether the planets themselves formed from it instead of merely using it as transport. The evidence therefore points more strongly towards second-generation formation. In this interpretation, the neutron star existed before Draugr became a finished planet. Material settled into a disk around the compact remnant, cooled enough for solid particles to appear, and eventually assembled into the 3 known worlds. Calling them second-generation planets does not tell us where the disk material came from. Several possible sources remain, and the differences between them are substantial. One proposed source is supernova fallback. During a stellar explosion, most of the ejected material moves outward and escapes. Some matter may fail to reach escape speed. It can slow, fall back toward the neutron star, and form a rotating disk if it carries enough angular momentum. The disk would contain elements created and mixed inside the original massive star. As it spread and cooled, solid material could condense and begin forming planets. This is the most literal version of planets built from the ashes. Parts of the star are expelled. Some of those parts return, and a new planetary system develops from the debris. It is an appealing sequence because destruction and construction belong to the same event. The supernova produces the neutron star and supplies the raw material for the planets around it. Detailed disk models have shown that fallback material can, under some assumptions, spread into the inner few astronomical units and leave enough solids to create the 3 known planets. Simulations published by Thane Curry and Brad Hansen found that supernova fallback disks could concentrate planet-forming material within approximately 1 or 2 astronomical units. Their models also found that the gas would disperse relatively quickly, making giant gas planets unlikely while allowing terrestrial bodies to assemble from the solids left behind. This produces a family broadly like the one observed, rocky-scale planets rather than Jupiters, all packed into the inner region around the pulsar. Draugr's low mass could reflect a limited supply of solid material near the disk's inner edge, while the larger planets grew where more matter accumulated. The explanation is plausible enough to remain part of the discussion. Fallback does not solve every problem. Material returning directly toward a neutron star may possess too little angular momentum to form a broad disk, at the distances of the known planets. Much of it may remain close to the pulsar, become extremely hot, and fall onto the neutron star before planets can develop. For the model to work, enough material must move outward to roughly Draugr's, poltergeist's, and Phobator's present orbits, while remaining massive enough to produce several Earth masses of solid bodies. Different calculations have reached different conclusions because the result depends on uncertain starting conditions. The amount of fallback, its angular momentum, its chemical composition, the disk's viscosity, the rate of mass loss, and the speed at which dust settles all affect the outcome. One model can produce sufficient solids, while another finds that most of the mass remains too close to the neutron star or is lost before it reaches the planet-forming region. Later simulations of terrestrial planet assembly found that low angular momentum disks associated with fallback could reproduce some of the observed planetary masses and eccentricities. Curiously, models with a more solar-like mixture of material performed better in some respects than disks composed almost entirely of heavy elements. Even the strongest simulations had difficulty producing a system as compact as the real one, showing that a promising origin story may still fail to match every detail. Lich's motion through the galaxy adds pressure to the fallback explanation. Precise radio astrometry measured a distance of about 710 parsecs and a transverse speed of roughly 326 km per second. Such a high speed suggests that the neutron star received a substantial kick during its formation. A strong asymmetric explosion is not the easiest environment in which to retain a large, orderly fallback disk. The researchers who measured that motion concluded that the planet-forming disk was more likely to have come from the evaporation or disruption of a binary companion. That leads to a second broad possibility. Lich may once have had another star beside it. The neutron star could have pulled material from this companion, forming an accretion disk. As the gas spiraled inward, it transferred angular momentum and accelerated the neutron star's rotation. This recycling process provides a natural explanation for why Lich spins once every 6.2 milliseconds. Old neutron stars generally slow down, so a very rapid millisecond pulsar usually carries evidence that a companion fed it material. The companion did not survive in its original form. No star is observed orbiting Lich today. It may have lost most of its mass gradually, been evaporated by the pulsar's radiation, or been disrupted during a close interaction. Some of the released matter could have remained in orbit around the neutron star rather than falling directly onto it or escaping. That material could spread into a disk and later form planets. Models proposed soon after the discovery showed how planet formation might occur during mass transfer in a low-mass X-ray binary, or after the pulsar began eroding its companion. In those scenarios, the same interaction that spins up the neutron star also provides a source of planet-forming material. Once the companion becomes sufficiently small or is removed entirely, the pulsar is left with a disk instead of a star. This explanation connects several observations without requiring the current planets to survive the original supernova. The neutron star can first form, perhaps while remaining in a binary. Much later, material from the companion spins it up and creates a disk. Draugr and the larger planets then assemble after the most violent explosion has already passed. They still form in a dangerous environment, but they do not have to sit through the birth of the neutron star as completed worlds. The timing of these events could be separated by a long interval. Lich may have existed as a slower neutron star before mass transfer began. The planets would then be younger than the neutron star itself. We normally think of a star forming first and its planets following soon afterward, but a recycled pulsar system does not need to obey that schedule. A stellar remnant can receive new material long after its original formation, and that material can create a new disk. A companion-fed disk might also provide more angular momentum than fallback material. Matter removed from a star already orbiting the neutron star carries substantial orbital motion. When the companion is disrupted, its debris can naturally occupy a broad disk rather than dropping almost directly onto the pulsar. This makes it easier to place solid material at distances of several tenths of an astronomical unit. One particularly detailed version involves a white dwarf. A white dwarf is the dense remnant left by a lower mass star, and many white dwarfs contain interiors dominated by carbon and oxygen. In the proposed scenario, Litch once orbited such an object. The orbit gradually changed until the white dwarf came close enough to be torn apart by the neutron star's tidal gravity. The destroyed white dwarf would form a thick debris disk. Some of the material would flow inward and spin up the neutron star. Other material would move outward as the disk redistributed angular momentum. As the outer disk expanded and cooled, carbon and oxygen-rich solids could condense. Those solids might collect rapidly into planetesimals and then into planets. This model was developed in detail by Ben Margalit and Brian Metzger. Their calculations found that, under plausible assumptions about disk viscosity and early mass loss, enough material could remain near the observed planet-forming region to create the PSR B1257+12 system. The same event could supply enough accretion to spin Litch to its observed millisecond period. The rarity of neutron star and white dwarf mergers could also help explain why confirmed pulsar planetary systems are uncommon. A carbon and oxygen disk would give Draugr unusual ingredients. Rather than being built from material with a composition similar to the young solar system, it might contain a much larger fraction of carbon. Under high pressure, carbon inside the planets could form diamond. This is the source of the suggestion that Litch's planets may possess diamond-rich interiors. The statement is a prediction of one formation model, not an observation of sparkling surfaces. The white dwarf merger model has attractive features, but it's not the only explanation consistent with the broad facts. No surviving disk spectrum has shown that the original material was carbon-rich. No measurement of Draugr's density has revealed a diamond-dominated interior. The current planets tell us their masses and orbital behaviour, but they do not identify the former companion that may have supplied their material. A less dramatic companion disruption process could also create the disk. A low-mass ordinary star may have been gradually stripped rather than swallowed in a single merger. Pulsar radiation can heat a companion and drive material from its surface. Systems known as black widow pulsars show neutron stars actively eroding small stellar companions. If that process continues far enough, the companion may be reduced or destroyed, leaving gas and debris that could contribute to planet formation. The material in this case would not necessarily be carbon-dominated. Its chemistry would depend on the type of companion and which layers were removed. Gas from an ordinary star could contain a composition closer to the material that forms familiar rocky planets. Draugr might then be largely silicate and metal, even though it still formed after the neutron star. Whichever source supplied the disk, a difficult transition had to occur. A disk created by fallback, mass transfer, or tidal disruption begins hot. Material close to a neutron star may be ionized and moving rapidly. Radiation and accretion can keep the inner region at temperatures too high for solid grains to survive. Planets cannot assemble until parts of the disk cool enough for atoms to form stable solids. Cooling changes the disk from a flow of hot gas into a place where dust can exist. Tiny grains settle toward the disk's central plane. Collisions cause some grains to stick, while others break apart. Given enough solid material and favourable conditions, the grains grow into larger aggregates. Those become planetesimals, bodies large enough for gravity to influence further growth. The process then becomes increasingly violent. Planetesimals collide and merge into planetary embryos. The embryos disturb one another's orbits and compete for material. Some move inward or outward through interactions with the remaining disk. Others strike the neutron star, escape, or merge into larger planets. A family containing one very small world and two much larger ones can emerge from an uneven distribution of solids and a long series of collisions. Draugr may have formed in a region where very little matter remained. The inner disk could have been depleted as gas and solids moved toward Litch. High temperatures may have limited the materials able to condense there. A small embryo could have survived without gathering enough neighbouring material to become Earth-sized. It might also be the remaining core of a larger body damaged by collisions. Early planetary systems contain many more objects than the final systems we observe. Impacts can remove mantles, scatter fragments, and merge several embryos into one. Draugr's present mass need not equal the mass it possessed at every earlier stage. Poltergeist and Phobetor evidently found more material. Their masses of several Earths suggest that substantial amounts of solid matter accumulated farther out. As they grew, they interacted with the disk and with each other. Their periods ended close to a 3:2 ratio, and their orbits became nearly coplanar and only mildly eccentric. Those properties preserve evidence of shared formation, even though the original disk is gone. The near alignment is one of the strongest arguments against independent capture. Capturing a free-floating planet around a neutron star is difficult because energy must be removed from the encounter. Capturing three bodies into compact, circular, nearly shared planes would require a carefully arranged sequence. Formation in one disk produces this organization naturally. The planets begin within the same flattened structure and retain much of that geometry after the gas disappears. A disk also helps explain the low eccentricities. Newly captured bodies often occupy elongated or tilted orbits. Gas and collisions can damp those motions, making the paths more circular. Poltergeist and Phobetor later continued to perturb each other, but the system remained dynamically stable because their masses and spacing prevented immediate disruption. Draugr's orbit is treated as essentially circular, though its low mass makes detailed dynamical measurements harder. If it formed in the same disk, its path would be expected to share approximately the same plane. The mass estimate commonly quoted for it relies partly on that family geometry. In this way, the proposed formation history even influences how astronomers translate the timing signal into a planetary mass. No existing observation identifies the exact moment when Draugr became a planet. There is no preserved image of the disk and no sample containing a date. The most scientists can do is compare the present system with the outcomes predicted by different models. Coplanarity favours disk formation. The pulsar's millisecond spin favours an earlier period of accretion from a companion. Its high velocity creates difficulties for simple fallback. Planet assembly simulations show that more than one type of disk can approach the observed result, but none reproduces every feature without uncertainty. The broad answer is therefore clearer than the detailed one. Draugr probably did not orbit the original massive star in its present form and calmly endure the supernova. The compact and organised planetary family is more consistent with worlds assembled in a disk after the neutron star formed. That disk may have included supernova fallback, but the disruption or evaporation of a formed companion is widely regarded as a stronger source. A neutron star and white dwarf merger provides one specific and well-developed version of that idea. Calling Draugr a planet built from ashes is close, though not always literal. Its material may not be the ash of the star that exploded. It may be the remains of a second star that fed the neutron star and was later destroyed. The present system could therefore be the result of two stellar histories. One star collapsed into Lich, while another supplied the disk from which Draugr, Poltergeist and Phobetor formed. This would make the planet's products of recycling on an astronomical scale. Matter spent millions or billions of years inside a star, was released through disruption, entered a disk around a neutron star, cooled into grains, and eventually became solid worlds. Draugr's atoms may have passed through stellar interiors before gathering into the small body now detected through radio timing. The sequence is violent, but the finished system is orderly. 3 planets follow stable paths. The pulsar rotates with remarkable regularity. The radio pulses arrive with small delays that can be predicted through orbital models. Whatever destruction created the raw material has long since ended, leaving behind a family that can persist for immense periods. Surviving as solid matter does not mean the planets offer mild conditions. The event that formed them may be in the past, but Lich remains active. Its rotation supplies a continuing wind of particles and high-energy radiation. Draugr occupies the closest known planetary orbit and has the weakest gravity of the three worlds, giving it the least ability to protect an atmosphere or replace material removed from its surface. Its origin tells us that planets can form beside a neutron star. The next question is, what can remain there after formation is complete? What Lich has been doing to Draugr throughout those short years depends on what we mean by survival. A planet can survive as an object while losing its atmosphere, its surface chemistry, and almost every condition normally associated with life. A mineral can survive radiation that would destroy a cell. A buried layer of rock can remain largely unchanged while the exposed surface is repeatedly struck by high-energy particles. When we ask whether anything could survive beside a pulsar, we therefore need to decide whether we're asking about the planet, an atmosphere, a complicated organic molecule, a microorganism, or someone standing outside with a folding chair and an optimistic amount of sunscreen. Draugr itself has clearly survived in the most basic sense. Its gravity continues to move the pulsar, and its timing signal continues to follow the expected 25-day orbit. It has not evaporated completely, broken apart under tidal forces, or fallen into Lich. NASA's catalogue still describes it as a confirmed terrestrial planet with about 0.02 Earth masses, an estimated radius of 0.338 Earth radii, and an orbit at roughly 0.19 astronomical units. The same catalogue warns that the pulsar planets are exposed to constant radiation from their host. Solid planetary material can be remarkably durable. Iron, silicate minerals, and carbon-rich compounds do not require comfortable temperatures, breathable gas, or protection from ultraviolet light in order to remain matter. Radiation can change their crystal structures and surface chemistry, but it does not make the entire planet disappear. A pulsar may be dangerous to biology while leaving billions of tons of rock quite capable of continuing around the same orbit. The surface would face several forms of energy. Lich sends out the radio emission that allows astronomers to time its rotation, but the radio waves are not necessarily the main threat to life. A pulsar also produces X-rays, gamma rays, magnetic fields, and a wind of relativistic particles. Most of the rotational energy lost by a millisecond pulsar is thought to leave through energetic particles and other high-energy emission, rather than through the small radio signal received by telescopes on Earth. The visible pulse is therefore less like the full output of a lighthouse, and more like one measurable item on a much longer and less welcoming electricity bill. PSR B1257+12 has been detected in X-rays with the Chandra X-ray Observatory. The first reported observation found only 25 photons from the source during an exposure of about 20,000 seconds. That is a faint signal, and the estimated X-ray luminosity was lower than that of most of the millisecond pulsars used for comparison. The low number does not make the system safe. Draugr lies extremely close to the pulsar by planetary standards, and even a modest high-energy output can matter when a planet receives it continuously over very long periods. Radiation intensity decreases with distance because the same output spreads across a larger area. Draugr is the innermost known planet, so it generally faces stronger exposure than Poltergeist and Phobator if the pulsar's energy is distributed broadly and evenly. The exact situation is complicated by beams, magnetic geometry, and the pulsar wind. Energy may be concentrated in some directions, and the planet's orbit may pass through regions of different particle density. We do not know the full three-dimensional relationship between Draugr's orbit and every component of Lich's emission. An atmosphere would provide one possible layer of protection. Earth's atmosphere absorbs much of the ultraviolet and X-ray radiation arriving from the Sun, while its magnetic field deflects many charged particles. The protection is not complete, but it allows the surface to remain far more stable than it would be in direct exposure to space. A thick atmosphere on a pulsar planet could absorb high-energy radiation in its upper layers and convert some of that energy into heat. The same absorption that protects the surface can threaten the atmosphere. When the upper gas receives enough energy, it expands. Atoms and molecules in the hottest layers may move fast enough to escape the planet's gravity. This can produce hydrodynamic escape, in which an outflowing upper atmosphere carries material into space. Charged particles from the pulsar wind can also remove atmospheric particles through collisions and electromagnetic interactions. Draugr is poorly equipped for this contest because of its low mass. A planet's ability to hold gas depends partly on surface gravity, temperature, molecular weight, and the amount of incoming energy. Draugr has more mass than the Moon, but far less than Earth. If its radius is close to the estimated value, its escape velocity would be substantially lower than Earth's. Light gases such as hydrogen and helium would be especially difficult to retain. Heavier gases would remain longer, but continual heating and particle bombardment could still remove them. A magnetic field might reduce some atmospheric loss by redirecting charged particles around the planet. It could also create regions where those particles enter near the magnetic poles, producing auroras. NASA artwork of the system has shown dramatic auroral displays caused by charged pulsar particles, but the images are illustrations rather than observations of actual skies. No magnetic field, aurora or atmosphere has been detected around Draugr. Magnetic protection is not a simple shield that blocks every problem. X-rays and gamma rays are not diverted by a planetary magnetic field in the same way as charged particles. A strong field can also channel particles toward particular regions, concentrating their effects. Whether it helps an atmosphere survive depends on the strength and shape of the field, the character of the pulsar wind, and the atmosphere's ability to cool and replace lost gas. Draugr might once have possessed a thicker atmosphere than it has now. Volcanic activity could have released gases from its interior during its youth. Impacts could have delivered volatile compounds. If the planet formed in a carbon-rich disk, carbon monoxide, carbon dioxide, and other carbon-bearing material might have contributed to an early atmosphere. If it formed from more familiar rocky material, water vapour, nitrogen compounds, and sulfur-bearing gases might have been present. The planet's small size means internal activity probably declined faster than it did on Earth. Smaller worlds lose heat more efficiently because they have more surface area compared with their volume. As the interior cools, volcanism and tectonic activity may weaken. An atmosphere being removed by the pulsar could then lose its main source of replacement. It would be like trying to keep a bath filled while the drain remains open and the tap gradually stops working. There is no observation showing that this happened. Draugr could have begun almost airless, particularly if the planet formed in a hot inner disk with few volatile materials. It could have gained a temporary atmosphere and lost it. A very thin exosphere may still surround it, supplied by sputtering impacts or material released from the surface. Mercury and the Moon both possess sparse exospheres, even though neither has a thick atmosphere. Something similar is possible around Draugr, but the timing method cannot detect it. The possibility of life becomes more difficult because life requires more than the survival of a few gases. It needs stable chemistry, usable energy, suitable temperatures, and some medium in which reactions can take place. Every known organism on Earth depends on liquid water, carbon-based chemistry, and environmental conditions that allow complex molecules to persist long enough to reproduce. The exposed surface of Draugr is an unlikely place for this. High-energy photons can break molecular bonds and ionize atoms. Energetic particles can pass through cells, damage genetic material, and create chemically reactive fragments. A thin or absent atmosphere would provide little shielding. Large temperature differences could occur between illuminated and sheltered regions, especially if the planet rotates slowly or keeps one side facing lich. There may also be very little ordinary light. Photosynthesis on Earth uses a large supply of visible photons from the sun. A pulsar releases energy in a very different spectrum. Radio waves are generally too low in energy for ordinary photosynthesis, while X-rays and gamma rays carry so much energy per photon that they tend to damage molecules rather than gently power familiar biological processes. An organism would need a different way to obtain energy. Life on Earth does not always rely directly on sunlight. Microbes near deep-sea vents use chemical reactions involving hydrogen, sulfur, iron, methane, and other substances. Organisms live beneath the seafloor, inside rocks, under Antarctic ice, and in underground water isolated from the surface for long periods. These examples show that darkness alone does not prevent life. They do not prove that life exists beneath Draugr's surface, but they identify the kind of shelter that would be needed. Rock is an effective radiation shield when enough of it lies between an organism and the source. A few centimeters can reduce some charged particle exposure, while meters or kilometers provide much stronger protection. Deep beneath Draugr's surface, the pulsar's X-rays and many incoming particles would no longer reach directly. Any environment there would be controlled more by the planet's internal heat, chemistry, pressure, and available liquids. This creates the least impossible habitat, not a glowing surface beneath the pulsar, but a sealed region underground. A buried pocket of liquid, perhaps warmed by radioactive decay or remaining internal heat, could in principle support chemical reactions away from the radiation. Minerals might provide nutrients and chemical energy. The overlying rock would provide shielding. Several large assumptions are hidden inside that picture. Draugr would need enough internal heat to prevent all liquids from freezing. It would need a useful solvent, suitable chemical ingredients, and pathways that bring those ingredients together. The planet would also need either to produce life independently or to receive living material from somewhere else. There is no evidence for underground water, current geological activity, organic chemistry, or biology on Draugr. The idea becomes even more difficult if the planet is extremely dry or dominated by metal and carbon. Liquid water might never have been available in large quantities. A diamond-rich interior would be scientifically interesting, but would not automatically provide the conditions needed for cells. Carbon is essential to known life, but a large supply of carbon does not create life by itself, just as a cupboard full of flour does not spontaneously become a bakery. The origin of life is separate from the survival of life. A microorganism already adapted to radiation and underground chemistry might endure conditions that would prevent complex organisms from functioning. Producing that microorganism from non-living chemistry could require a long period of environmental stability. If Draugr's early history involved intense radiation, impacts, atmospheric loss, and rapid cooling, the planet may never have offered a calm interval for life to begin. Material could theoretically arrive through impacts. Rocks ejected from Poltergeist or Forbitor might cross the system and strike Draugr. On Earth and Mars, impacts can launch pieces of crust into space, and some of those meteorites eventually reach the other planet. In the Lich system, exchanges between planets are conceivable if impacts are powerful enough and orbital paths line up correctly. This does not provide a convincing source of life, because we have no evidence that Poltergeist or Forbitor contain organisms. The larger planets have stronger gravity and may be better able to retain atmospheres. A scientific study of neutron star planets concluded that, depending on poorly constrained properties of the pulsar wind, the two super-Earths, around PSR B1257+12, could fall within a proposed neutron star habitable zone. The result applied to the larger planets and depended on thick atmospheres and uncertain energy transfer processes. It did not establish that either world is habitable, and it did not place tiny Draugr in the same favourable position. A habitable zone around a neutron star is not the familiar ring shown around a sun-like star. For ordinary stars, the concept often begins with visible and infrared energy, heating a planet enough for liquid surface water. Around a neutron star, high-energy radiation and particle winds may provide the heating. The same energy that keeps water from freezing can also remove an atmosphere or damage biological molecules. Habitability depends on how effectively the atmosphere absorbs, redistributes, and survives that energy. A thick atmosphere can behave like armour and a heating system at the same time. High-energy particles deposit energy in its upper layers. Circulation moves some heat around the planet. Dense gas increases surface pressure, allowing liquid water over a wider temperature range. If atmospheric loss is slow enough, the environment might remain stable for long periods. The two larger planets have masses of about 4 Earths, giving them a much stronger gravitational grip on gas than Draugr. Researchers could therefore construct cases in which their atmospheres lasted for billions of years. The results changed greatly depending on the assumed efficiency of the pulsar wind in heating and eroding the gas. This uncertainty is large because pulsar winds are difficult to measure and may behave differently from the simpler, evenly distributed flow used in introductory calculations. Draugr begins at a disadvantage on almost every relevant measure. It is smaller, closer to the pulsar, and less able to retain gas. A thick atmosphere would represent a greater fraction of its total mass, and losing that gas would be easier. Even if Poltergeist and Phobator occupied narrow ranges of possible habitability, the same calculations would not automatically extend inward to their much lighter sibling. This does not reduce the scientific importance of Draugr. Habitability is only one question that can be asked about a planet. A sterile world can reveal how atmospheres escape, how rocks respond to energetic particles, how planetary systems form from disrupted stellar material, and how small bodies remain stable around compact objects. Mercury, Venus, and the Moon are not known to support life, yet each has transformed our understanding of planetary evolution. The word survive can therefore be answered in layers. The planet survives, its orbit survives, its minerals survive, although their exposed surfaces are probably altered. A substantial atmosphere may not survive easily, but its absence has not been directly proved. Complex surface life appears extremely unlikely under the expected radiation conditions. Microbial life deep underground is physically easier to imagine, but there is no evidence that the necessary water, energy, chemistry, or organisms exist. A human visitor would need far more than a spacesuit designed for the Moon or Mars. Protection would have to reduce high-energy radiation and particle exposure, manage uncertain surface temperatures, provide all air and water, and operate without useful sunlight. A base would probably need to be buried deeply or constructed behind thick shielding. Electronics would also require protection because energetic particles can damage circuits and corrupt memory. Reaching the planet presents a more immediate obstacle. Lich lies about 2,000 light-years away. Even a spacecraft moving at speeds far beyond those achieved by current missions would need an immense length of time to arrive. No detailed mission design can overcome the fact that the target is distant, invisible, and known mainly through radio timing. Draugr is a world for remote measurement, not a destination waiting for the next launch window. This distance protects us from its environment, while also limiting what we can learn. A telescope on Earth cannot sample the surface, lower an instrument through an atmosphere, or drill beneath the crust. Improved radio timing may refine the orbit and mass. Better X-ray and gamma-ray observations may describe Lich's output. New theoretical models may narrow the range of atmospheric survival. Direct evidence of life would require an observational signal that we do not currently know how to obtain from such a small and unusual planet. The honest answer is therefore less dramatic than a simple yes or no. Rock survives beneath a pulsar's glow. A planet can remain intact for billions of years. An atmosphere might survive if it is massive enough and protected under suitable conditions, particularly on the larger planets. Life on Draugr's surface is difficult to support with anything currently known. Life deep below the surface cannot be ruled out through timing data alone, but it requires several unconfirmed features and should not be treated as likely. Draugr does not need to be alive to matter. Its continued presence tells us that planet formation can follow stellar death. Its weak gravity tells us that pulsar timing can reveal objects much smaller than Earth. Its unknown surface reminds us that detecting a planet and understanding a planet are not the same achievement. From Earth, we know the schedule of its year more confidently than we know whether it has a single enduring pocket of gas. That difference brings the investigation back to what Draugr has contributed without ever becoming visible. It has not given astronomers a photograph, a spectrum, or a sign of biology. It has given them a repeating delay in radio pulses, a measured mass, a short orbit, and a place within the first confirmed planetary family beyond the Sun. Those modest pieces of evidence have been enough to alter the boundaries of where planets can form, how small a detected planet can be, and what kinds of systems deserve to be searched. Those boundaries are the main reason Draugr remains important. It is not the easiest exoplanet to illustrate, the most promising place to search for life, or the closest world outside the solar system. It does not have a measured atmosphere, a visible surface, or a convenient star providing familiar daylight. Its contribution is quieter. Draugr demonstrates that a very small planet can exist beside a stellar remnant and reveal itself through nothing more than the effect of its gravity on an exceptionally regular signal. When the search for planets beyond the solar system began producing reliable results, many astronomers expected the first examples to appear around ordinary stars. The solar system offered the only known model, so it was natural to search for other systems containing bright stars, giant planets, and orbital arrangements that looked at least vaguely familiar. The first confirmed exoplanets, instead, appeared around PSR B1257+12. Poltergeist and Phobetor were reported in 1992, and the tiny inner planet followed in 1994. NASA continues to recognize the pulsar system as the location of the first confirmed exoplanets. This beginning warned astronomers not to confuse familiarity with possibility. A planet does not require a yellow star. It does not have to orbit at a distance where liquid water could exist. It does not need to be large enough for an ordinary telescope to notice. It can form after a star has died, circle a neutron star hundreds of times smaller in diameter than the Sun, and remain hidden except for a pattern measured in microseconds. The discovery method is part of the lesson. Most known exoplanets have been detected by transits, or by the motion they cause in ordinary stars. A transit measures the slight reduction in starlight when a planet passes between the star and the observer. Radial velocity measures the spectral shift caused by the star moving toward and away from Earth. Pulsar timing follows the same gravitational principle through a different signal. The planet moves its host, and the changing position of that host changes when its pulses arrive. Draugr shows the extraordinary lower reach of that method. A planet containing about 2% of Earth's mass produces only a small wobble in an object assumed to contain more mass than the Sun. The two bodies are badly mismatched. Lich dominates the system, yet Draugr still moves it by enough for the timing data to reveal the orbit. A gravitational effect does not have to be large if the clock used to measure it is stable enough. The phrase, lightest planet in the universe, remains useful as a title, though it needs the usual scientific caution. Draugr is one of the lowest mass confirmed exoplanets known. It is not necessarily the lightest planet that exists. The galaxy may contain enormous numbers of bodies smaller than Draugr that our instruments cannot detect. Some may orbit ordinary stars, others may travel around white dwarfs, neutron stars, or no star at all. Detection records describe the abilities of observers as much as they describe nature. The largest planets were easier to find because they produce larger signals. As instruments and methods improved, smaller planets became accessible. Draugr reached an unusually low mass early because pulsar timing offered sensitivity that other techniques had not yet achieved. Its place in the record arose from both its physical properties and the fortunate behaviour of its host. This should not make the discovery sound accidental. Astronomers still had to observe the pulsar repeatedly, construct a timing model, correct for Earth's movement and the interstellar medium, identify several overlapping periods, and test whether the signals behaved like planetary orbits. The planets did not announce themselves with an image. They emerged after other explanations were examined, and the timing patterns continued to repeat. Poltergeist and Phobator provided the strongest confirmation because their gravity altered each other's orbits in the predicted way. Their interaction showed that the periodic signals came from real planetary mass bodies. Draugr's weaker signature then extended the system inward to a body near the mass scale of the largest moons. The family became both the first confirmed exoplanetary system and one of the most unusual. The three names can make the system seem deliberately arranged for a story. Lich sits at the centre. Draugr moves closest to it. Poltergeist and Phobator follow farther out. The names came much later than the discoveries, but they describe a real connection to stellar death. Whatever exact process created the planets, their current host is the remaining core of a star that no longer exists in its former state. That history changes the meaning of planetary formation. Around the Sun, the planets are usually described as byproducts of star formation. A cloud collapsed. The Sun formed in the centre, and material in the surrounding disk gradually became planets. The process happened once, early in the system's history. Around Lich, the available evidence supports a more complicated sequence, in which planet formation may have occurred after the neutron star already existed. A stellar system can therefore receive another opportunity to produce worlds. Material from a supernova, an accretion disk, or a disrupted companion can settle around a compact remnant. The disk can cool, form dust, create planetesimals, and build planets. The original star may be gone, and any original planets may be gone with it, but matter remains available for another arrangement. This recycling does not require intentional planning. Gravity, angular momentum, cooling, and collisions are enough. Gas spreads through a disk because inner material moves inward while angular momentum is transferred outward. Dust settles. Solid particles meet. Some collisions destroy objects, while others allow them to grow. After enough time, a new planetary family can remain where a binary star or an expanding supernova once dominated the system. Draugr may contain atoms that spent earlier portions of their existence inside a star. Some of its iron, carbon, oxygen, silicon, or other elements may have been processed through nuclear reactions before entering the planet-forming disk. Earth contains elements produced in generations of older stars as well, so the general idea is not unique. The unusual part is the possibility that Draugr formed directly from the remains of a companion, associated with the neutron star now at the centre of its orbit. Its exact composition remains open. A rocky and metallic structure is plausible. A carbon-rich body is possible if the disk came from a disrupted carbon and oxygen white dwarf. A high-density remnant shaped by collisions cannot be excluded. Each option preserves a different part of the system's past, but the timing signal cannot distinguish between them. This limit is worth remembering because exoplanet discoveries are sometimes presented as though every new name represents a fully described world. Usually the first detection supplies a small set of measurements, an orbital period, a mass, a radius, or some combination of them. The familiar image of a planet is then produced by an artist using scientific constraints and reasonable guesses. Draugr has a particularly large gap between the security of its orbit and the uncertainty of its appearance. We know it completes 1 year in about 25.3 Earth days. We know it moves roughly 0.19 astronomical units from Lich. We estimate that it contains about 0.02 Earth masses. We classify it as terrestrial because that mass range is consistent with a solid planetary body. We do not know the colour of the ground, the exact diameter, the length of the day, the presence of an atmosphere, or the pattern of radiation across the surface. This mixture of precision and ignorance is normal in astronomy. The motion of a distant body can sometimes be measured better than its basic appearance. Gravity acts predictably across enormous distances, While light from a small dark object may be too weak to isolate, the orbit becomes a set of numbers with several decimal places, while the surface remains an empty space in the description. The result is not unsatisfying when the two kinds of knowledge are kept separate. An orbit is not a substitute for a photograph, but it is still evidence. Mass is not composition, but it still places the planet within a useful physical range. Uncertainty does not erase the discovery. It defines the next questions. Draugr also reminds us that planets do not exist for the purpose of supporting life. Human interest naturally moves toward worlds with water, atmospheres and temperatures resembling Earth's. Those targets deserve attention because they may help answer whether life exists elsewhere. They are not the only worlds capable of teaching us something. An airless planet beside a pulsar can test models of atmospheric erosion. A carbon-rich planet could reveal a route to planetary chemistry unlike our own. A compact family around a neutron star can show how disks behave after stellar disruption. A very low-mass planet can demonstrate the sensitivity of a detection technique. None of these contributions depends on a forest, an ocean, or even one living cell. Our own solar system makes the same point. Venus explains how a rocky planet can develop an extreme greenhouse atmosphere. Mars preserves evidence of climate loss. Mercury shows the results of forming or evolving close to a star. The Moon records impacts and early solar system history. The value of a planet lies partly in how it differs from the others. Draugr's difference begins with scale. It is light compared with Earth, but massive compared with the objects of ordinary experience. The phrase tiny planet refers to its position within a range extending from asteroids to gas giants. It is not a grain of dust. It is a rounded planetary body that may be several thousand kilometers wide, carrying more mass than the Moon while completing 14 local years during one Earth year. Its host creates another scale problem. Lich may contain more mass than the Sun, while measuring only a few tens of kilometers across. Draugr circles an object physically smaller than many cities but gravitationally capable of controlling an entire planetary family. The central body is small enough to disappear from a simple diagram unless enlarged, while its mass determines the speed of every planet around it. The pulsar's rotation adds an even faster scale. Lich turns roughly 161 times each second. During one Draugr year, it rotates hundreds of millions of times. During the years that radio pulses travel from the system to Earth, the pulsar completes an almost unmanageable number of rotations, each one gradually contributing to a signal that can be received by a telescope and compared with the expected schedule. None of those pulses carries a picture of Draugr. The planet is encoded in their timing. It slightly shortens and lengthens the route travelled by the radio waves as its gravity moves Lich toward and away from Earth. The entire world appears in the data as a regular instruction to adjust the clock by a few microseconds. There is something practical in this example. Scientific discovery often begins with an indirect effect. Electrons were inferred before they could be imaged. Black holes were studied through the motion and radiation of surrounding matter. Dark matter is named for something that does not emit the light needed for direct observation. Draugr belongs to the same broad habit of finding unseen things through the changes they cause in visible or measurable ones. This approach requires patience because indirect evidence can be mistaken. A timing signal may come from an incorrect position, a clock problem, interstellar plasma, or behavior inside the pulsar. Researchers must test those possibilities rather than selecting the most interesting explanation. The strength of the Lich system came from repeated timing and from the detected interactions of the larger planets. After those checks, the invisible system became reliable enough to change the history of astronomy. The first confirmed exoplanets did not appear as dots beside another star. They arrived as deviations from a predicted schedule, the discovery that expanded the known population of planets beyond the solar system began with a clock that seemed to run early and late. Since then, exoplanets have appeared in a wide range of settings. Some orbit 2 stars. Some complete an orbit in less than a day. Some travel on highly elongated paths. Some are larger than Jupiter, while others are closer to Earth in size. Atmospheres have been detected, temperatures estimated, and entire systems studied through transits and gravitational interactions. The field has become far larger than the 3 planets around Lich, but those planets still mark the point at which confirmed planetary systems stopped being limited to the Sun. Draugr occupies the smallest corner of that first family. Its signal was weaker than those of Poltergeist and Phobator, and its physical nature remains less constrained. That is precisely why it belongs in the story. It shows that the system was not merely capable of producing 2 substantial super-Earths. It also produced or preserved a world only modestly heavier than the Moon. The existence of such a small inner body places demands on formation models. Material must have reached the correct distance from the pulsar. Some of it must have remained solid or cooled into solids. The growing body must have avoided falling inward, colliding with a larger planet or being ejected. It then had to remain in a stable orbit while the pulsar continued losing rotational energy. Every model that attempts to explain the family must account for this small survivor along with the larger planets. A theory that easily forms several Earth-mass objects but leaves nothing near Draugr's orbit is incomplete. A theory that produces one inner fragment but cannot explain the Kepler outer pair also falls short. The smallest member can therefore provide a constraint out of proportion to its mass. The same principle applies to searches elsewhere. Small objects can reveal missing details in the history of a system. An asteroid belt can show where a planet failed to form. A moon can preserve evidence of migration or collision. A minor planet can indicate that solid material survived around a white dwarf. Focusing only on the largest bodies gives a simpler picture, but it may leave out the events that shaped them. Draugr also changes the idea of what it means for a planetary system to end. The death of a star can destroy planets, release them into interstellar space, or leave them on altered orbits. It can also provide material that becomes another disk. A system can pass through stellar death and still contain organized planetary motion afterward. The new arrangement may be hostile, but it is not chaotic. Draugr, Poltergeist, and Phobator follow stable, measurable paths. Lich spins with enough consistency to act as a clock. Gravity continues working in the same dependable way, even though the objects involved are unfamiliar. That dependability is what allows us to understand the system from such a distance. The radio pulses follow the laws of electromagnetism while crossing interstellar space. The planets and pulsar follow gravity. Atomic clocks on Earth record arrival times. Mathematical models connect the observations with orbital motion. No single part of this process requires a person to see the planet. We began with a world described as the lightest planet in the universe. The more careful description is one of the lightest confirmed exoplanets, detected because its small mass repeatedly moved a much larger neutron star. That qualification does not make the planet less interesting. It places the achievement where it belongs, at the meeting point between a tiny gravitational signal and an exceptionally sensitive method. Along the way, Draugr has led us through the collapse of massive stars, the creation of neutron stars, radio pulses, timing residuals, planetary masses, short orbits, unusual formation disks, possible carbon-rich interiors, atmospheric escape, and the limits of habitability. The planet itself has remained invisible throughout. We have learned about it by following the effects it cannot avoid producing. Now, as the system continues moving through the galaxy, Draugr completes another orbit every 25 days. Poltergeist and Phobator travel along their wider paths. Lich rotates more than 100 times each second, gradually slowing by an amount too small to notice without careful measurements. Radio waves leave the system and begin the journey toward Earth. Some of the pulses reaching our telescopes now began travelling long before modern astronomy existed. During their journey, people developed clocks, built radio receivers, learned what neutron stars were, and eventually constructed instruments precise enough to notice that the pulses were arriving slightly early and late. The planet was present throughout. What changed was our ability to recognize its effect. That may be the most useful lesson offered by the smallest worlds. Nature does not become more or less real according to whether we can detect it. Objects remain in orbit, signals continue traveling, and physical processes continue without waiting for observers. Discovery occurs when a measurement becomes precise enough to reveal what was already there. As you return to the room around you, the world beneath you is many times more massive than Draugr and receives its energy from a far calmer star. Earth has a thick atmosphere, a protective magnetic field, liquid oceans, and a surface where life has continued for billions of years. None of those conditions should be treated as automatic features of a planet. Draugr shows how different the word world can become. Perhaps it is still late where you are. Perhaps the local time has moved farther into the night since we began. You have remained in one room while the Earth has continued rotating, the Moon has continued around Earth, and every planet in the solar system has advanced slightly through its own orbit. Far away, Draugr has moved through another small part of its 25-day year. If this journey helped you relax or gave you a new way to think about the planets that remain hidden beyond ordinary sight, you can like the video and subscribe to Science for Sleep. You can also leave a comment with where you're listening from and what time it is there now. It is a simple way to see how many places on Earth have joined the same discussion about a planet none of us will ever view directly. There is no need to hold on to every number. Draugr will continue its orbit whether we remember 0.02 Earth masses or not. Lich will keep rotating without requiring us to count the pulses. The timing models can remain with the astronomers and their computers. For now, it is enough to know that a very small planet travels beside the remains of a dead star, and that its gravity was strong enough to cross 2,000 light-years as a measurable change in time. The signal was quiet, but it repeated. Astronomers listened carefully, recognized the pattern, and found a world. Let the remaining details settle without arranging them. The pulsar can keep its rapid clock. Draugr can continue its short year. Earth can carry you gently through the night at its own familiar pace. Sleep well, fellow traveller, wherever you are listening from, and whatever time your clock happens to show.